Hi, my name is Bob Teasley. I'm the Customer Service Manager for Light Flat Roll Products. And today I'd like to talk to you for a few minutes about that. In 1993, we formed 2 business units in the corporation. And those business units are here at Burns Harbor and at Sparrows Point out in Baltimore, Maryland. And our intention at that point was to try and bring together all the organizations that made producing steel and delivering steel and selling steel as much as possible together in one organization, and that's what we've done in creating those business units. The functions that were consolidated under the commercial organization were customer service, field sales, which is not located at the plant, marketing, which is here, outside processing, production applications, production scheduling, and transportation. The functions that were remaining at corporate are claims process, billing and accounts receivable, export sales, and corporate transportation. Basically, the way we divided up the country was somewhere about mid-Ohio and along this line here. Anything east of that is basically Sparrows Point's area, and everything west of that is basically handled by Burns Harbor. And most of our concentration is right in this area right here. We have a little bit of West Coast. We have some down here in the Houston, Dallas area. But most of ours is concentrated in the Midwest area and the southern area. As I mentioned, these are the different departments and areas that we communicate with in customer service on a daily basis. So as you call us and you ask us questions or inquiry about things, these are the types of folks that we get involved with in trying to answer those types of questions. Accounting is a very minor point. We do things like part costing and things like that related to specifically cost issues or inventory issues. Whenever we have physical inventories outside the plant, we use their auditing function to go out and make sure that things are happening the way that our data shows that they're happening, that things are being recorded as they're happening. Corporate billing, they handle, that's still corporate invoices. Any kind of what we call e-letters, which are any kind of problems with invoices that have already been sent out. PDRs, which is our price deviation reports, and that just means that's how we can account for how much we price on a part or bill on a part. Adjustments, EDI functions are handled corporately. Credit is now here locally. They came to us in August of '95. And so all the credit's done here for Burns Harbor at the plant. Marketing, customer service is part of the marketing group. Production scheduling is in the same office complex with customer service, and they'll be talking to you next. Operating, of course, out in the mill. Transportation is in this building now, and then we also have some corporate transportation functions. Outside processing and logistics, what they handle for us is communicating with all the processors and storage locations outside the mill, making sure that they're communicating with us, that we're doing things the way our procedures have them outlined, or doing any expediting. They handle things like setting up service agreements, status, if we need some kind of status on when something's going to process, scheduling types of functions, expediting, delivery, inventory management. And then we sometimes talk directly with processors and warehouses. If we need something released for shipping, we handle that kind of function. So we'll talk directly with them for those types of things. Quality assurance, they help us with material inspection and disposition. They do the processor and warehouse audits along with accounting. They advise us on transportation methods, of which method would be the lowest cost for us and the customer. They handle any corrective action, claims, and education for the processors of how our process works and how our orders are set up. Product applications is a special group that handles things like finding out what type of steel we need for a particular application. So they'll come into your facilities, they'll work with your operating people and with your metallurgical people, and they'll talk about the part, and they'll try and work out what type of steel we need. So they advise the plant marketing group and the metallurgical group on what type of steel is required for a particular application. And we have 3 people here at the plant now that go out and do specific applications for non-automotive. Then we have a group in Detroit that handles the automotive side of it. Sales, as you know, they're out in the field. They come and visit you. They try and help us resolve problems, get answers to whatever types of questions we might have, as well as bring information back to the plant. We're broken into 2 groups in customer service. The plate group, which handles all the plate products and strip plate product, and strip plate product starts at, I think it's like 017 or something gauge, or 0167 or something like that. Is whenever you use cut-to-length type product off of our hot mill at I think it's 0167, it starts and it's called strip plate, and that's handled in the plate marketing group. We handle all the coils and lifts, the lift being under 0167. In the light flat rolled side of the business, we have 9 CSARs dedicated to automotive, 4 in the central region, 4 plus a supervisor doing entry in the Midwest region, and the southern and eastern are handled by 4 CSARs and a supervisor. And then we have 3 on-site teams where they physically set at the customer's site. These are 3 different GM plants, and they do their work on site. So they're working directly with the customer every day. And those are large volume type customers is where we implement that kind of solution. We handle estimated about 176,000 phone calls a year, and that's roughly about 30 a day per person. 32,000 orders we enter per year, and we change about 136,000. We support 3 plants. Burns Harbor and Lackawanna are our primary plants that we support, but we also enter orders for the Sparrows Point plant for those customers who would like to deal with 1 customer service person and they have some Sparrows Point business. If their primary business is done at Sparrows Point, then Sparrows Point generally handles the entry for the minor work done at Burns Harbor or Lackawanna. If it's equally split, it's kind of a toss-up, and we go with whatever the sales group or the marketing group thinks is the best way to do it. But generally, there's some clear distinction on which plant would better serve the customer. And so we try and work it out that way. We have about 350 customers that are active at any one time that we ship to directly. We support 6 district offices and 50 sales reps. Our primary responsibilities, of course, customer contact, supporting the sales group, supporting the operating and staff departments, doing inquiries for the customer and the sales group, managing entry versus the sales plan. Sales plan being what we allocate to every customer based on what's negotiated at the beginning of the year, so that we don't overload the facility. So we have to try and balance the tons we have. We are responsible for order entry and J-mix analysis, and I'll talk a little bit about J-mix in a moment. And then we're responsible, of course, for order status. If you call and ask us for information, or you want a daily listing or a weekly listing or something like that of your orders and where they are in the process, we put those together. Expediting with production, scheduling, transportation, or outside services, we do those kinds of functions. We call those groups. They help us get this material through the process and hopefully out of here in a timely manner. And then we're responsible for J-mix analysis and inventory management. Talk about our order management process a little bit. Basically what happens is a customer will give us an order of some type, either we'll receive it fax or in the mail, and we'll take that order and we'll review our products for sale, make sure that it makes sense. If it has to be inquired, we'll take that step and we'll inquiry it with the plants to make sure that they can make that type of product. And then we review the business plan to make sure that this is not going to go over some customer's sales plan allocation or wherever we're at that particular point to keep the facility in balance. If all that looks okay and there's open schedule space, we enter the order. If it's not okay, then we get back to you and we try and work out some kind of negotiated type of change to the order. If everything's going okay, the order gets dressed. This is done by some people out in our mills who physically look at all the parameters on the order, what we're capable of doing, and decide how to dress that order. And dressing the order means putting on all the mill operating instructions, any kind of packaging instructions, any kind of things that we need are done in that MET dressing process so that we can communicate what you want to the mill. And then after that, it goes through a facility load system, which takes that information and tries to put on each of the major units how many tons that's going to mean to that unit. So then that's how we keep track on a week basis of how many tons we've loaded into the facility. And then there's several things that happen there. It goes through calculations and some other things, which just gives it things like how much slab weight is required, what are going to be the mill aims to achieve your gauge, those types of things. And then there's a person in our group who reviews what facility load produced and said was the load on the mill, and then that person adjusts the schedules. Then this all happens, and what happens in the process is marketing will go to the sales group and say, we're open for May, which they've done here just recently. And so now we start taking all May orders into the process, and we put those May orders on the books. And then we're trying to balance out the month of May in our operation and see how that fits across the operation. So these folks here, what they do is they look at those orders coming in and they adjust them by week and make some decision about where they fit in the picture. And at that point, there's an acknowledgement letter sent out to the customer, and that's when you get your first notice, which all of this happens within about 24 to 36 hours. So between the receipt of the order and this actual acknowledgement letter is tended to be less than 24 hours. Probably some of it goes as much as 36 before we acknowledge the order back to you. So when we say we're open for business for a particular month, we're taking those orders and we're entering them into the system, and then within 24 hours of that entry basically is the target. You should get an acknowledgement letter back telling you that that order's in the system and what the date was. Then there's this period called variable number of weeks here. And that's depending on how full our facility is, how well we're running. If things are running well, that period should be small if the order book's not overbooked. And it gets overbooked because we may have a fall down in the operations, and therefore we didn't run as many tons as we expected, so now we have more in this window here than we can physically run in that period. So then that'll expand out a little. We'll take that order and we'll push it out. And then marketing, after that variable number of weeks, which could be anywhere from 3 to 6 weeks, depending on what happens, we'll actually go in and firm up the schedule the week before they melt the steel. So we'll actually go in and firm up the orders. So we might be, in our tandem mill, we might be taking 30,000 tons a week, and we may have 35 in that week. And so we have to decide at that point which 30,000 are going to get into the process. And so that's how that process works. And so when we firm that up, the very next week the manufacturing cycle begins, and then that's when it gets melted. The following week it gets hot rolled, and Pete, who's going to be up next, will talk to you a little bit about that. And then the last part of the process, of course, is the billing. 2 ways we get orders into the process. The first way is that we get your purchase orders from you, and you tell us the dates and all the information that you want us to have about that order. The second way is a system we have called JMix, where we receive forecasts from customers, and the customer tells us through a forecast how much steel he's going to use on a given date in a given week. So in the week, these are Monday dates, so in the week with Monday at 10/16, they're going to use 23 tons on this part, and then again in the week of 10/30, they're going to use 45 tons and so forth. We try and put orders on the books ourselves of where we think that'll generate the right inventory level. And so generally our level, it just depends on the product. This is a cold roll class 2 product, and depending on the product, we'll run different number of weeks. But that's what we're attempting to do. And you can see here they had enough tons on the books here that they could take a couple of weeks without entry, and so they did that and made an adjustment. And so we're making that decision internally based on those forecasts, and that's part of our responsibility in working with those types of customers that send us forecasts rather than purchase orders. Yes?
Would that be like a grouping of customers?
No, this would be a single part. There's a part ID there, which is not showing up very well. there's a part ID there. That's a single part that we do that for, and a customer tells us what the part is, and then rather than give us purchase orders, we work off of blanket orders, which there's the blanket order number, and we just take the forecast in and we make decisions based on the forecast of where we'll enter the tons. And so it simplifies the process greatly because of the fact that we don't have to have all this purchase order paperwork in the process and try and match a specific amount on a specific date. Those types of problems go away with our JMix types of accounts. So it makes it much easier for us, and I think it makes it much easier for the customers because they don't have to deal with all that paperwork also. And then the thing that it does, though, is it makes your measurement process a little more difficult. It puts the responsibility for measuring whether we're delivering back on us. And so we have to monitor those kinds of things. And so it's more of a passive system in measuring the performance. A shutdown is obviously the worst measurement, but we generally are watching the inventory weeks, and we're trying to keep the orders on the books to maintain those weeks. It doesn't mean the steel gets melted any differently than it does when you get a purchase order. It just means that we're responsible for that process of order entry. And so we use that most of the automotive is on blanket orders. A few of them are still on purchase orders. The process works much simpler for everybody in this forecasting type of process. Those are basically the things I wanted to talk to you about. I'll take any questions that you have, and then we can move on to our next speaker if there are no questions. Any questions? Okay. Thank you very much.
Our department is basically broken up into two functions. One is planning, and this falls under the superintendent and staff, and the responsibilities here include system development, special projects, conversion coordination, customer service, and an overall plant scheduling coordination. The other function is more detail-oriented, and it's done by we have scheduling representatives at each one of the mills and in the transportation department. Their responsibilities include inventory application and control, unit scheduling, mill load making, expediting, and customer service. In the arena of transportation, their responsibilities are ordering and routing trucks, weighing trucks, ordering rail cars, and coordinating barge movements. Next, I'd like to walk through this order flow. Basically, it's from order entry to shipping, and I think it'll give you a good idea of production scheduling's role within this process. The first step of the process is order entry, and Bob talked about that. It's done by our customer service representatives. The next step is the facility load system. Now, this system is critical because it does a couple very important things. Bob also mentioned this. It assigns a customer ship-by date, and that's based on a desired date of the customer. And it also assigns some critical information to the orders, such as the information in all the operations need to know to produce the order to the customer specifications. Now, once the order has passed through facility load, it's what we call release to production. And this is the first time that production scheduling sees this order. And our first step, the first thing we try to do is we try to find an application. And this can be done in a couple of ways, systemized or manual. Systemized way, we have a system called auto providing. And what this system does, it goes through and it interrogates the inventory, and it tries to find a stock application for every order. Anything that the system cannot find a home for falls into the lap of who we call providers. And they go through, and they also have the same responsibility providing stock to these orders. Now, if we do find an application for an order, what we do is we attach that material to the order, and obviously it would bypass any of the operations that the stock has already completed. If we can't find an application for the order, Then we send that order over to the first operation, which is steelmaking. Okay? At that point, they go through and they custom make every order that's sent to them. Now, the process of communicating to our operations what to make and when to make it is done through our detailed scheduling systems. We have a detailed schedule system for every unit in the plant. We have scheduling clerks at every mill, and they work with these scheduling systems. And what they do is they generate a detailed schedule based on customer ship by and the unique scheduling constraints of each unit. Now, when I say scheduling constraint, I'm talking about things such as width and grade and gauge. I think there's something like 18 scheduling constraints that can come into play at any particular unit. These sequence rules have been established over the years, basically to maximize or optimize quality and maximize productivity. Now, once the order has flowed through the predetermined sequence of operations, now it comes into our warehouse. And it falls upon production scheduling's responsibility to go through and manifest this material. And once again, we have an automatic system to take care of this. It's called auto load. It goes through and it maps up rail loads and truckloads and sends that data onto our transportation department. Transportation, like I mentioned earlier, also falls under production scheduling. They have the obligation of going in and get the proper equipment in for these loads that are manifested. And we do this through one of two ways also. It's automated, and we have some people who also do this function. Auto dispatch, what happens is we take all the loads manifested in our warehouse, send it to our trucking companies, let the trucking companies send some detail back to us, and reserve times in each one of our mills to come pick up the loads. I know I went through this pretty quickly and I didn't get into any detail. Basically, I just wanted to convey that production scheduling, we start when an order is released to production, and our obligation, our responsibilities are not fulfilled until we get equipment in to ship the order to the customer. Any questions? Yes, sir.
What's the lead time now for cold roll?
For regular cold roll product, something like this where I have 4 operations, basically it's a week for each one of these. It's a week for order entry and facility load. It would be another week for steel making, a week for hot mill, a week for cold mill, pickler and tandem mill, and a week for hot dip. Any other questions? Okay, thank you.
Okay. Good afternoon. My name is John Batiste. I'm Quality Assurance at Burns Harbor, Assistant Superintendent. I have the steel making, plate mill, hot mill areas under my tutelage. What I'm going to cover today, this afternoon, in the next 15-20 minutes is how we manage quality at the Burns Harbor plant. Essentially what we start with is we have our quality policy. Essentially in our quality policy is essentially 3 main functions to it. Number 1, that we will manufacture our products with agreed to specifications with our customers and using standard operating procedures in our plant. The second one is that as a plant we will continuously strive to improve our products. And number 3, that we be customer driven, that we're always looking to see what the customers are looking for out in the future. And essentially it's like a never-ending process. Once we see what the customer's looking for in the future, then we go back, look at our products, and essentially come up with new products that we then require new standards for. One of the main things in our management of quality is our quality assurance manual. Essentially, they cover all the various aspects of quality, from our quality system to how we handle orders, how we handle purchase materials, our training procedures, process control, how we handle inspection and quality records, non-conforming material, down to how we do audits through our plant. essentially our quality manual then can be cross-referenced against various industry quality standards. Of course, QS 9000 being one of the big ones that here at the plant, we are QS 9000 qualified. So we strive to make sure that our quality manual is up to speed with all the industry requirements. As far as how we drive this total quality, what we have, we use various tools. One of them, when we're looking for new equipment, is we use the quality function deployment system in order to look at what customers are really looking for in their products, and then getting that back to what that relates to in our equipment. As far as then our process, we use FEMA's failure mode effect analysis tools, statistical capabilities. We have a lot of employee involvement. As I go through, you'll see we have various teams in our operations. And then as far as the day-to-day control, a variety of things. We have an annual quality plan that's developed every year. As I mentioned, the SOPs, do a lot of control charting, product auditing, and process auditing through our process. And then down into problem-solving techniques. As far as I mentioned, our quality planning, what we usually do at the beginning, near the end of each year, is we'll sit down, each division will set up a quality plan for the following year. Essentially what we'll look at is our process, our flow charts, our control plans, see where our problems have been in the past. Normally we will do Pareto analysis of both our claims and in-house problems and set up teams to attack those, as was shown there. And then through the year, then we monitor the progress a variety of ways. One thing we have here is each month, each area of the mill has a quality meeting with the general manager, president, and we review our quality plan, where we stand, any problems we've run into, and corrective actions. As far as the daily quality monitoring, some of the things we have the daily quality calls. We really like to do customer visits. We have our technical service engineers who make visits to the plant, but we also feel it's very important that we get the people from the plant at our customers' facilities. A lot more emphasis to our people is if they can visibly see it versus the customer technical service engineer coming back and trying to explain it. So we try where we can to have customer visits. As I mentioned, we have quality system audits, both internal. One of our sections of our department is what's called our quality systems group, and what they do each year is they audit half our plant. So half our plant each year is audited by our internal quality system group. The other half of the plant each year is audited by our corporate quality system group. So not only do we have our every 6-month audit from our QS 9000 audit, but we also do a full plant audit each year, either internally or from corporate. As I mentioned earlier, one of the other things we do we do product audits. In all our mills, we have audits set up to audit the product, collect a lot more information than what can be obtained from various normal inspection techniques, and use that to really characterize our products. In the coal mill, we do what's called a QC audit, where we'll run random coils that the computer picks across the line, run at slow speed with 2 inspectors, and what we collect from that is various surface data, plus we take front and back tests to characterize our property data. And this has really helped us over the years, both in property improvements, surface improvements, and also microstructural improvements. We also do process audits to look at our processes. As I said, testing and inspection. And one thing that's really increased a lot in the last few years has been corrective action, both coming from the customers, such as yourself, asking for corrective action. And we also instituted an internal corrective action procedure where, say, we have problems from our caster to our plate mill area. The plate mill can initiate a corrective action to the caster for those type problems, such as, say, we made a cast where we had extensive cracking that required reconditioning. They can send a corrective action through our system back to the caster, requiring them to respond.
Is that an informal process, John, or you know, on your in-plant corrective action, like between the caster and the plate mill, or?
No, it's actually what we have. It's a computer system where it's put in, say the plate mill puts it into the system, and it's given a set time for response back from the caster, and then a set time for closure. And one thing we do is, if those dates are not met, as I mentioned, we have this monthly quality meeting upstairs of our president's office. Those items that are past due have to be reviewed by that department. And that's something we felt was needed because the informal didn't seem to get the emphasis that it really needs. As I said, some of the customer service groups we have our in-mill technical service engineers who will call on the customers. We also have a variety of other people who can call on customers in need. Our product application group to come look at various parts, make some suggestions as far as grading. Our research department has I know, visited a lot of the customers that are here today in areas such as welding, burning, techniques such as that. We also have our in-mill operating and technical groups. And as I mentioned, we have in a lot of our areas we have our continuous improvement teams, which are both salaried and hourly people. And some of these, especially say in our coal mill, we've had very good success with our hourly quality team, going out to some of our automotive customers, and they just have a certain technique that they can get down on the floor, talk to the people, and really get some good information that helps us solving problems.
Is that done on a volunteer basis or by appointment? Or?
As far as the hourly involvement in that, it is an appointed position, but it's appointed by the union. But the union understands the importance of it, so it's not per se a position that is done by political. Our coal mill team, as I mentioned, we have a roller from the tandem mill, we have a mechanic, we have a quality person, and we have an operator from another unit, and they're all extremely good people. One of the things in the past few years that we've tried to change is our technical service engineer, who in the past, previously, his only function was to be a claims taker. And a lot of times they felt that what their function was to try to defend material that, say, was not of the best quality. So what we try to do is eliminate that as being their responsibility, and try to get them more into the mode where we feel their function now is to really go out, look at the customer's operation, come back with, what are the quality requirements, what are the problems, act as a problem solver, and then get down into the claims. We've initiated a lot of small claims policies where most of the time now we don't even have a person going in just to handle claims. The claims is handled through the system automatically, and the person is mainly going in to really look at the operation and try to improve. As I mentioned, in order for this whole system to work, we also need our hourly people to be involved. What we have is we have what's called unit coordinators for each of our groups that acts as a coordinator with the quality team, getting suggestions from the floor to help us in our operation. The quality team, as I mentioned, one of their main functions is both be an in-house communicator to the people on the floor and also to make customer visits when we have some problems, get down on the customer's floor and see if some of their techniques and expertise might help. And another big thing is our safety teams, which really, I'm not sure if a lot of you have heard of some of the problems we've had recently, but we really feel comfortable about our safety teams. In fact, they have just developed a new safety program that we're in the process of getting initiated right now. One of the other big areas is just training of all our people. A lot of opportunity for on-the-job training, various seminars that we send our people to, in-house training. We continue to have our SPC training, our design and experiment, other technical training. And one thing we really started in the last few years is training more and more people on financial management, so they understand the business, what is important, why when we say we have to run an operation like this, why financially that is required. And one of the other important things in this whole quality arena is facility improvements. And Burns Harbor has spent an extensive amount of money modernizing the facility. Even though it was the newest integrated mill to be built, it's now over 30 years old. So things have improved in 30 years. So we have spent a lot of money in the last few years in various areas. Number one, we've rebuilt our number 2 battery, which again makes it self-sufficient for coke. Continue our relines of our blast furnace. And one of the things we did in our last reline was put coal injection on our furnaces. And what that does for us, that allows us to replace some of the coke with this fine powdered coal, improves the performance of the furnace. Steel making, where really our refining really starts. Spent a lot of money over the years, steel ladle desulfurization, allowing bottom pour ingots for those plate type products that require it. This is one big thing for our light flat roll and plate is hot metal desulfurization. Previous years desulfurization was made in the vessel. Now essentially all our desulfurization is done in the hot metal. So we're already starting, when we charge the hot metal into the BOF vessel, down at levels of 0.004, 0.003 sulfur in a lot of cases. Ladle metallurgy stations, that allows us for real tight control in the chemistries. The vacuum degasser for some of the new products we're coming out with, the ultra low carbon and plate degasser. And one thing we initiated last year, Burns Harbor has always been has always had more finishing capacity than it does steelmaking capacity. So over the years, we're always out needing semi-finished product in the form of slabs. One of the things we did the third quarter of last year, we started what's called a large heat project. We essentially replaced all our ladles with larger ladles, so we went from a heat size of about 280 tons up to a heat size now of about 305 tons. So each heat is now 25 tons greater, but when we're making 18,000 heats, that adds up to essentially another 400,000 tons of steel that we do not need then to go out and purchase. As we get into finishing ends, some of the work we've done in our hot mill area, we've worked on our reheat furnace, 3D profile gauge, and right now we're right in the midst of our hot mill modernization. We just put in the new loopers. We're in the process. This quarter we'll be putting in our shape gauge on the hot mill, and also we'll be putting in the hydraulic gauge control in the last few stands of the hot mill. At that point, we're really looking at what's the next step. We have money approved. At this point, though, we're looking at, is the money better spent on heavy roll bending earlier in the finishing train or on a fourth furnace? That's one thing we're looking at right now, where we're going to get our best improvement in gauge control and profile control, either from the heavy bending or from a more uniformly heated slab. So at this point, we haven't made that decision yet. We have certain monies available, and we're in the stages of making that final decision. In the plate mill area, we're just finishing up really our last step of our modernization there. We did a complete upgrade of our furnace, computer controlled. One of the things we put in a few years back is our cold scarfing machine, which helps us upgrade slabs that had minor mold level deviations on our caster. We have a continuous online thickness gauge. This has allowed us to take some orders of very precise weight placed for the shipbuilding industry. One facility we're right in the process right now of starting up is our accelerated cooling facility in the plate mill, where we'll be able to, by using accelerated cooling, make higher strength grades, and also take one chemistry and make a variety of different grades based on how we cool it. One thing that isn't mentioned here, one of the other items we did put in last year was a new heavy leveler, which allows us to improve our flatness. And in our cold mill, some of the things we've done there, we modernized our tandem mill. We put a computer system on our batch anneal for optimization, various shape controls on our temper mill. A few years back, we put our hot dip galvanized line in, which allows us to make, essentially put in to make exposed galvanneal type product. Roll grinder modernization for our roll grinding facilities. One thing we're in the process right now, just groundbreaking, is a new filter control system for our tandem mill, which we think will really improve our performance on roll marks off our tandem mill. Customers now, such as are getting extremely tight on roll marks that you visibly can't see but can pick up by stoning. And we feel that this new filter system we're putting in will help us eliminate some of these real fine marks that we might get. And in our galvanized products division up at Lackawanna, we've done some work there on both our tandem mill and our furnace to allow us to improve the quality. As far as the equipment, that's one area. The other area is how we test it. And we also have spent money in our labs. Our chemical lab, we put some new X-ray spectrometers in. This X-ray spectrometer we have in our BOF was essentially done for our interstitial free product. One of the variables we found that was extremely critical for quality on the interstitial free product is to control the percent FeO in our slag. And you think, well, what does that matter? You're making steel, but by controlling your slag chemistry really affects your quality of the final product. So what we had to do is put a new X-ray in, test the slag, actually get slag samples off the ladle, test it, and then modify the slag to get our FeO levels extremely low, and that dramatically improved our quality of the final product. In our plate mill, we spent some money on our new impact machine. As we're getting in the accelerated cooling, some of these higher quality grades of steel, the old machine we had, which was a 256 foot-pound machine, these new grades would essentially stop the hammer. They're so tough that you couldn't break them, so we had to go to a larger machine. Our cold mill, we put a metallographic lab. We bought a scanning electron microscope. As we're getting into some sophisticated coatings, we needed a piece of equipment that quickly we can measure the percent alloy layers. In previous years, we had to send these samples back to our Homer research, what might take a week or so to get the analysis. Now we could get it very quickly. We also put an image analyzer in there, and we put a new lab in when we started up our hot dip line. And then finally, what did all this do for us? As far as quality certificates and awards, a variety of awards we have obtained. We are ISO and QS 9000 qualified. And our latest certificate, which we just received, will qualify us, I believe, through 1999. We're 4Q1, GM Targets for Excellence. In fact, we were the 1995 GM Supplier of the Year. On the plate side, we're both ABS and API qualified, and Caterpillar and a variety of other customer certificates we have obtained. As far as looking at historical data, you can say to yourself, okay, you have all these tools in place, what has it done for you? I think if you look at our claims performance, we saw a dramatic improvement. One thing you have to remember, what happened back in this period, from 81 to 82 was when most people started switching in the automotive end from zinc or metal to electrogalvanized. And we saw from that switch a dramatic increase in our claims costs as we got those processes up and running and got the controls in place. But since that period, we've had a trend downward or improvement in our claims performance. And if we look at our in-house rejects, I think we're seeing two things here in our in-house rejects. we saw a dramatic improvement, a slight improvement, and now we're starting to see a slight increase here. What we are seeing here is we made a dramatic improvements and then our gradual improvements. In the last few years, some of the customer requirements and some of our product lines have outpaced our improvements. And we're right now in, especially in our plate end of our business and our hot roll, really looking seriously at how we're processing. We feel in our cold roll end we have made dramatic improvements, but we're seeing on the plate end where now customers want a plate surface with no grind marks. On the hot roll side, such as SOS, very quality conscious customer, we have seen that we're at this point re-looking at our processes and have changed some of our processes because of the quality requirements people have. So that's one area we're working on, and I think positive to say that the next few years this trend will start coming back down again. Our goal for this year on, good question there, and good comment there. What we're seeing from customers right now is, depending on the industry, the automotive end is looking at levels where they want 1,000 ppm, which is 0.01 reject levels. You have people in, or 0.1. You have people in other industries that their quality levels aren't as tight. Our goal for in-house this year is to be 2.57. As far as our claims for this upcoming year is 0.55. Right now, after the first 2 months, we're meeting the claims performance. We're at about 0.42, but our in-house is still slightly over 3. So we still have not met the goal yet, but we have seen an improvement from last year where we were. Yes?
Your prior bar chart up there with the claims loss, could you define what that is? I'm not really sure what you're trying to depict there.
What this is claims loss as a percent of selling value. So what this is saying is that at 0.6, that means 60 cents of every $100. So if we sold products that we sold it for $100, it meant in claims we paid 60 cents. That as a claim.
And define claim for me. I'm not really sure. You ship something that's rejected by the customer, or is that a claim?
It could be either something that's rejected by the customer, or if the customer, say, had to do extra processing, which we then compensated them for extra processing. We've had customers who, they have a product, they burned it out, it went out of flat, so they then take it and level it, and say we compensate them for that leveling. That would be part of that.
Would a claim also be, if you had a blanket contract to supply a certain type of steel, and you were unable to meet the schedule, causing the customer to go out into the spot buy market? The difference between the blanket contract with you and the spot buy, is that a claim that's billed back to you?
If the customer came back and charged us for that added cost, yes. Any other questions? Okay, thank you.
For those of you who don't know me, who didn't meet me last night, I'm Pete Hollingsworth. I'm the supervisor for quality assurance practice development for our cold roll and coated products. This morning I'll discuss with you the cold mill. We'll go through the equipment in the cold mill and describe its purpose and help give you a feeling for the influence that each of those pieces of equipment can have on our product. We've got an hour and a half for this session, so I encourage you to ask questions as we go along. Depending upon the time frame, if we've got some time left over, I can get into some product characteristics comparing CQ and DQ and high strengths and some of those interesting issues. But we'll take that part as we have time available. Okay? So with that, let's get started. The coal mill is comprised of many separate and unique areas. We'll go through just about every one of these areas. We're going to start at the picklers, but please note, in this schematic of the coal mill, we have tandem mill, which is coal reduction mill, hot dip coating line. Dave Funk will follow me at 9 o'clock and discuss the hot dip coating line. We've got anneal facilities, we've got skin mill facilities, and we've got a finishing end. Okay? So we'll discuss all of this. But we're going to start off with the picklers because that's the first operation in the coal mill. The picklers, as you see here, are fed by the hot mill. A hot roll product, the hot bands, are our raw material. As the schematic shows, we have two picklers at the coal mill. The primary purpose of the pickler is to remove oxide. Bottom line, it's to remove the oxide. If we didn't have to remove oxide, we wouldn't have to pickle. When you were in the hot mill yesterday, you observed when the slabs came out of the furnace, they had a scale jacket on them. And that scale jacket was caused by the slabs at elevated temperatures in contact with air. Through the roughing mills, you noticed that we used a lot of high pressure water to spray that scale off. We removed it. At the end of the hot rolling facility, you saw coils, the band getting coiled up. And the temperature there is typically over 1,000 degrees. When the coil is sitting in that form at 1,000 degrees, it is oxidizing. The pickling operation is intended to remove that oxide. The oxide that occurs from the end of the finishing into the coil. If we don't remove that oxide, it's going to get pressed in later on in the coal reduction process. It's going to cause an imperfection, which is unacceptable for exposed application. So pickling operation is there to remove the oxide. While we're pickling it, we're also going to take advantage of some other things that we can do at that time. We're going to trim the coil edges with rotary trimming knives. We'll do that in this operation. For the majority of our products, this is where we'll make the width of the coil. If the product requires width tolerances tighter than the standard ASTM, we would elect to trim it after all of the processing. But just for that tolerance, we can trim it here in the pickler and finish with a product in tolerance. Okay? So we'll trim the coil here. We cut coils to size. We can take big coils and make them smaller, or we can make small coils and weld them together and make big coils. We're trying to take advantage of economies of scale and to match the coil weight out of the pickler with the coil weight that you as customer is asking for. Okay. Let's just take an example. Yeah, Tim.
On this one here, where you're pickling it, you have to unroll the entire coil to do everything that you're talking about?
Yes. The question is, when we pickle it, do we have to unroll the coil? And as we get into the pickler, we'll realize, I'll show you that it's a continuous pickler, which means that we pull one coil through, decoil it, pull it through, attach it to the coil behind it, and do the same thing with the coil behind it as a continuous motion. Okay. But that process gets us to the joining of coils. Let's just assume you're looking for a 20-ton coil. And it's to our advantage in the hot mill to make 50-ton coils. Okay. Because of size, economies of scale. We can approach take the 50-ton, cut it down to two 20-ton coils, and throw 10 tons away. Or we can take two 50-ton coils, join them together, and cut 5 20s. minimizing scrap, maximizing our economies of scale, making a more efficient process for everyone. Okay? So we can join coils up, or we can cut them down.
Manufacturer takes it, so you have to pay any attention to that?
The question is, what about the weld? What do we do with it? When we're joining coils, we're going to leave the weld in, the pickle weld in, only if the application will tolerate that weld. Okay, there are some applications that don't tolerate those welds. Exposed applications won't tolerate that weld, as you're going to have a line through your panel. It's unacceptable. Some severe drawing operations won't permit that weld. But for most unexposed applications, that weld will be fine. Okay, so depending upon the application, we'll leave the weld in and build coils up, or we aren't permitted to weld and build. Okay. No, it's an electric resistant butt weld. Okay, and if necessary, we can oil the coils. Some of the product we sell off of the picklers is our hot roll pickle product. Some folks like that oil to keep it from rusting. We'll oil it here at the picklers. Let's look at the pickler a little bit now. Let's look at the equipment itself. Now the pickler is about 1/4 of a mile long. For the purpose of this schematic, we put it into 3 sections. It's actually, this is the front of it, this is the middle of it, and this is the tail of it here, okay? So that belongs there, and this belongs over here. It's one long continuous facility. Okay. But we're going to go through the major pieces of equipment here, just so you get a feel for what we're trying to do. Okay. The front end of the pickler has got payoff mandrels. It's got 2 of them, and a welder. It's got 2 payoff mandrels. One mandrel is paying off the coil which is currently in the pickler. The second one has got a coil on it which is being prepared. The ends are being cut and squared and cleaned to be welded onto the coil in front of it. Okay? These are continuous picklers, which mean that you join one coil to the next one and you pull it through. Okay? As opposed to a push-pull pickler, you go in and you go out. Then bring on another coil. You go in and you go out. This isn't like this. It's continuous, one coil after another. It goes in one end, it comes out the other end, and it's never supposed to stop in the pickle bass. Okay? It's a continuous process. So we got the 2 mandrels. One's getting ready to be joined and one's being paid off into the pickler. We've got our welders to join the coils, an electric resistant weld. We join the coils, we pull it through, and then it goes through a cold reduction mill. The cold reduction mill we call a bliss mill. It's meant to give the steel a small reduction, of anywhere between 1 to 2%. The purpose of that reduction is to break the scale. Scale, or iron oxide, is very brittle. It does not stretch. Steel, hot roll steel, does stretch. So if you reduce the steel a little bit, 1 to 2%, you're going to stretch the steel and it's going to crack the scale. With that scale being cracked in that fashion, it allows the later pickling process to attack the scale from more than one direction. It allows us the pickling acid to get down into the scale cracks and down underneath. So it increases the pickleability, if you will. For those of you who purchase hot roll skin pass, hot roll pickle skin pass, we can perform that skin pass with that reduction mill there, so that we don't necessarily have to take it to a standalone unit. There's some economies there that we'll take advantage of. After we skin pass it, or scale break it, put it through the bliss mill, you may have heard any one of those terms, the coil will travel down into an accumulator. This is a horizontal accumulator underneath the acid tanks. The acid tanks are, for this pickler, are about 15 feet in the air. When you get into the pickler, look up. You'll see the tanks. At eye level, you'll see these horizontal accumulators. The horizontal accumulators do nothing more than inventory the strip so that you can stop the front end of the line and continue to feed strip into the pickle tanks. And the process works that you have some looper cars at one end with rolls on them, and these cars travel back and forth underneath the pickle tanks. And they're firmly attached at the other end. Imagine yarns between your fingers. Your fingers are stretched out this far and you've got yarn between them. As you pull together, you've got extra yarn. It's the same concept here. Put the rolls together and you have extra steel. That steel, when the front end of the line stops, the rolls come together and you take that steel and continue to put that steel into the pickle tank so that you can continuously travel through the pickle tank while stopping the front end of the line. Okay? And when the front end of the line starts going again, the rolls start to pull apart and you start to inventory more strip. Okay, so when you're in the pickler, you'll look at eye level and you'll see cars going back and forth with strip between them. Okay? Yep.
Pete, everything that goes to the cold roll status, does it have to go through pickling?
Yes. Yes. We'll come out of the looper storage area and into the pickle tanks. Here we have 4 tanks. They're brick lined. They contain hydrochloric acid. Each tank has a little different pH to it, a little different iron concentration to it. It all is involved in the science of pickling. Key here is to keep the strip moving through the tanks without stopping. If the strip stops in the tank, the acid, once it finishes eating the scale away, will start to attack the strip. That's a condition we call over-pickled. It looks like the strip is etched. It's basically, for cosmetic type applications, unacceptable. Once we go through the pickle tanks, and this is where we are removing the scale, we go to an elaborate rinse area. Several rinse tanks, sprays, wipe-offs. It's very important that when the pickling operation is complete, that all of the acid get removed. If we don't remove the acid, the strip will rust later on. It'll rust later on because we're using hydrochloric acid, lots of chlorides. Chlorides have an affinity for moisture. Any chloride that is left on the strip will soak up any available moisture in the atmosphere. It'll also pull moisture through slushing oil. It's important that it be removed. If it's not removed through this rinse, it'll rust. Interesting to note, you can rinse it and leave the water on. If there's no chloride, it'll take a lot longer to rust just with that water than it will with a chloride on there that's been dried off. So it's an interesting phenomenon. But we rinse it. After we rinse it, we go into another looper storage area. Again, it's horizontal. Same principle as under the tanks. You got to inventory strip so that you can stop the exit end of the line. Okay? After we go through the looper storage, at this end of the line, we trim it to width with rotary trimming knives. We inspect it, we oil it, and we coil it. That product then can be delivered downstream to the tandem mill, or it can be delivered back to the hot mill for a hot roll pickle product.
In a lot of our applications, we purchase coil from you people, and we have a processor uncoil it and cut to length.
Mm-hmm.
And there are occasions, depending upon the application, where we have trouble with coil memory. Will this process do anything to relieve or reduce coil memory?
It should have little influence. Okay? If the winding tension down here is too extreme, it can influence that. That's pretty much the only opportunity. Okay? Pretty much the only opportunity there, but it really has to be extreme.
What's your total distance of your pickling tanks? The tanks themselves?
What's the distance of the tanks? I'm uncertain. Uncertain. The line itself is 1,200 feet long. My guess is the tanks are about a quarter of that. But the exact distance I'm uncertain of. Couple of the gotta-know statistics of the pickler. We do have two lines. Essentially, they're identical lines. Call them number 1 and number 2. They're 1,200 feet long. They go to about 1,000 foot per minute maximum for good speed. They handle our hot band product. These are hot band sizes now, 24 to 73 wide and 0.61 a quarter of an inch thick. Okay? So anything coming to a cold mill can go through these picklers. Some of the hot roll pickle product that we supply is beyond the thickness range here. In those cases, we'll secure a pickler outside of our grounds here that can do the job and process it there. And a couple of the more of the gotta-knows. We do carry temperature in the pickle baths, 190, 180 degrees. The hotter the acid, the greater the pickleability. Okay? The more reactive that is. You do have a problem if it gets too hot. We don't want the acid to boil. As soon as it boils, the pickleability goes down. You've got an environmental issue. Okay? So it's important to regulate the temperatures correctly. And it's also very important that you have the correct pH or acid concentration in each tank in this thing called iron concentration. We are eating iron oxide away. The iron's going to build up in the pickle acid. Okay. Any additional questions about the pickler before we leave them?
What happens to the iron that builds up?
Okay. Question is, what happens to the iron that's built up? The remaining acid it gets concentrated into a thing called pickle liquor. That can be removed from the tanks and recycled, and then the iron can be reclaimed from that. There's an outfit just down the road here called I want to say Iron Magnetics, who does just that. They purchase spent pickle liquor and they pull the iron out of it, and then they use that iron as to the right molecular structure to be using in the magnets. Pardon? Okay. Terry's interested in pickle stain, where we would pick up pickle stain. Pickle stain typically is from an oxidation of the strip after it's been through the pickle tanks. Okay? Either it's wet too long, it's not rinsed properly, or we get some sort of contamination with a hydraulic oil or something like that on the surface. But pickle stains that you see typically come after the pickle tanks. It could be moisture, could be moisture, could be a hydraulic fluid or some sort of a grease or things of that nature, or an oxide. A lot of times what's referred to as pickle stain is nothing more than a form of rust. Okay?
Yes. Pete, if everything going to cold roll needs to be pickled, is it also oiled?
Okay. If the product is going to the tandem mill for cold rolling, we'll put a cold rolling oil on it at the pickler. Okay? We need lubrication carried into the tandem mill for the reduction process. We'll put that oil on it right here. Okay? We'll put additional lubrication while we tandem roll it. If it's going to back to the hot mill as a hot roll pickle product that needs to be oil, we'll put a hot roll oil on it. Okay? So depending upon the application. Okay? So what for cold roll product, the oil that we're putting on isn't a slushing oil or is not a protection oil. It's it's an oil meant to provide lubrication for coal reduction. Which the residuals you won't see in the final product. When it's pickled, after it's pickled, we've got two choices. We can send it back as a hot roll pickle product, or we can send it into our tandem mill. This is the life and blood of the coal mill. It's got several names. We call it the tandem mill. It also can be referred to as a coal reduction mill or a 5-stand mill. Okay? Its sole purpose is to reduce the strip thickness. This is where we make thickness. We'll take the hot band, reduce it 60 to 80%, depending upon the product that we're building. That reduction will occur here in a 5-stand. All coal, hence the term coal reduction mill. We apply no heat, although much heat is generated through the reduction process. It's all internally generated. We also start to make the surface. In the coal reduction process, you need to have a surface which later on can be temper-rolled with a matte finish. Okay, so you start that process here. You also, if you don't do it right, if you can leave many blemishes here on the tandem mill, so that it's unacceptable. So you got to have a good strip surface-wise coming out of here with respect to mechanical marks, and you got to have the right texture coming out of the tandem mill for subsequent surface texturing for exposed applications, what we call matte finishes. But the primary thing here is to make thickness. Now the 5-stand mill is very similar to what you saw in the hot mill finishing. A hot mill, you saw a 7-stand finishing mill. 7 stands together, each stand with 4 rolls in it. Same thing, same principles here with a coal mill. Here we have 5 reduction mills. For this schematic, the mill housings and whatnot have been removed. Each stand with 4 rolls. 2 work rolls, those are the rolls that are in contact with the strip of small diameter, 25, 26, 27-inch diameter, backed up by what we call backup rolls of larger diameter. The purpose of the backup rolls is to provide structural rigidity for the work rolls. Imagine my pointer here is a work roll, or a backup roll. It doesn't matter for this purpose. We apply the force at the ends of the roll. We don't apply it uniformly across the roll. The reduction force is provided at the end of it. The strip is in the middle of the roll. When we press down or press up, depending upon if you're looking at top roll or bottom roll, it's going to bend. That strip in the middle, force on both sides. It happens in the hot mill. It happens in this mill. It'll happen later on in the temper mill. Okay? It's that bending that provides the crown of the strip, or the differential thickness across the width. Okay? That process starts in the hot mill. It's carried on through the cold mill. Okay? Imagine the forces required to bend a forged steel 26-inch diameter roll. It's astronomical. But those are the forces we're applying. Imagine even still the forces required to bend a 40-inch diameter steel roll, because those guys bend too. In the coal mill, we're actually not putting additional crown into the strip. In the coal mill, we're only trying to conform to the crown of the hot band. If we don't conform to that crown, then we'll roll, we'll differentially reduce the strip across the width, and we'll get shape problems. Okay. So here that we're trying to pretty much match that previously determined profile and not alter it. But if we don't have the rigidity in that mill, as we press down, we will roll the edges more than we will the center and cause problems. What you don't see on this mill is a thing called work roll bending. It was added to the mill about 10 years ago to, again, help control the reduction, the uniform reduction of the strip across the width. Work roll bending is nothing other than a torsional force applied at one of the rolls to try to straighten them out. If the roll is intending to bend this way because you've got force on the outer sides pushing down, work roll bending tries to provide torsional to straighten it out. Some mills, to control this whole thing, are now being built as 6-high mills. 2 backups on the top, 2 on the bottom, okay, with work roll bending. Those are the more modern mills. This is strictly a 4-high as it shows here. Strip comes in one end, it goes through each reduction stand, it comes out the exit end. It's just like you saw at the hot mill. Okay? We control the strip width with an X-ray gauge at center width. Okay? There's an X-ray gauge at the finish stand and one right here. The strip comes through, the X-ray reads how thick it is, it feeds it back to the computer. The computer adjusts the speeds, adjusts the roll gaps, the forces, the bending, etc. It's basically beyond the ability of a human to control the whole process and get an acceptable product out the back end. Elaborate process control scheme. Are there any questions about this facility and its intent? Yeah?
Is that crowning effect, is it in the roller itself or is that just natural?
Question is the crowning effect, is it in the rolls themselves or is it natural? George, I'm going to try to take a stab at this one. We intentionally roll or grind our rolls into a conical shape. So the rolls themselves are crowned, okay? But we crown the rolls to help the whole process minimize the ultimate crown that we have, okay? So that we intentionally put crown into the rolls, but that's only, the center is bigger because we know the ends are going to go down. So if the center is bigger and the ends go down, you kind of flatten the profile out. So even though we put shape into the rolls, the crown that you see on the strip isn't because we put that shape in. It's because of the forces applied to the outer sides of the rolls. Okay? Yeah?
A couple of the problems we have when we have a couple like smaller diameter or something, you have a quarter inch. But we have problems with edge weight, oil can. Is this where that problem would be caused?
Larry's asking the shape difficulties that he sees, some edge wave, some oiling can. Is this where those shape issues are? Basically, yes, they are. Imagine, if you will, a strip coming into the tandem mill, and we try to roll the edges more than the center. Okay, this is a reduction process. As you're rolling it and making it thinner, the steel's got to go somewhere. Okay? And it's all attached. But if you reduce the edges more than you reduce the center, you've got to start visualizing this now. The edges are going to get longer than the center, right? I mean, if you reduce the edge 50% and the center only 40%, you're making more length on the edge. But where's the steel going to go? It's attached to the center. It goes up and it down and up and down and up and down, creating edge wave. Okay? Center buckle or oil canning. It's just the opposite. You're moving more strip in the center than you are the edges. You're making it longer in the center. Steel's got to go someplace. It's all attached, so it distorts itself in the center. And that's why it's so important that this cold roll line operation do nothing more than match the crowns that are coming in. Because if you try to manipulate that crown and change the relative crown across the width, you're going to end up rolling either more in the center or in the quarter or on the edges, creating those shape problems. Okay? Yeah, Alberto.
Yeah, Peter, I've heard the term roll marks. What do you refer with that?
Okay. Question is roll marks. What is the term, and is it influenced by this? Yes. A roll mark is nothing more than a damaged roll, work roll, in contact with the strip surface. Okay? If you have a bruise here, a dip, or a protrusion in the roll, when it goes across the strip surface, it's going to leave that impression on the strip surface. That's called a roll mark. So it can happen on any of these work rolls. If it happens up here, it's going to pretty much be gone by the time it comes out the end, because you're still reducing the strip, and it's going to flatten out that mark. But as those things happen further down the line here, the likelihood that they're going to get erased or rolled over is minimized. So that if you have a mark on stand 5, it will provide a visual, unacceptable roll mark on the surface. Stand 4, since we're giving it about 5% reduction here, if it's a very light roll mark, it'll cover up. If it's not so light, it'll be hard to see, but when you go to form it, it'll still be there. Okay? Each one of these rolls, since we're reducing it more and more as the strip goes through, will leave a different repeat. Okay, there we got a 25-inch roll. If the mark's here, and it marks a strip every revolution, it ought to be every 78 inches. Okay? But if it occurs here, you've got the 78 inches plus a 5% reduction here, so it's going to be every 81 inches. If it happens up here, since you have massive reduction in this strip, about every 150 inches. Okay? As the roll mark occurs farther back in the train, the more difficult it is to see because of the subsequent reductions. Okay? Yeah, Tom.
Pete, how do you pick up the roll mark defects in that process?
Okay.
Pick it up later down the process?
If we do our job correctly, no, we'll pick it up here. Okay? Question Tom asks is, how do we pick up the roll mark defect? How do we know that it's there? Okay? When we're rolling exposed products, we have a procedure here in a tandem mill which basically it says every third coil that we produce is taken off a line, taken out of the product stream. It is unwrapped. We take about 5 wraps off of it and then take 2 lengths that are about 8 feet long, 8 to 10 feet long each wrap. Okay, 8 to 10 feet long to get these 2 distances here. And we stone those. We stone the top and we stone the bottom, and we look for the roll mark. Okay? If we see a roll mark with that inspection procedure, we'll stop the process and we'll change the rolls, the offending roll. And we'll know which roll it is by measuring the repeat distance. Okay? So that's our procedure for catching them. If we do that correctly, we should see them here. I will say that over the past 4 months, we have changed that procedure to what it is today. 5 months ago, it was every 5th coil, and we didn't use an abrasive stone to help highlight. It was strictly a visual issue, and every 5th coil. With the standards, and some of them are in your facility, Tom, with the standards which are being applied today, we found the need to be more critical in this area to help find them here, things that we weren't seeing previous. Yeah, Terry.
There's no really visual inspection at the end of the what's actually running.
Okay. No, there is. This facility here is traveling about 4,000 foot per minute, and when you go there, hopefully it'll be operating today, you'll see that there's lots of fluids being applied between stands. You really do not have the opportunity to see the strip closely while it's being produced. At this end, where the strip is being coiled, it's protected. Occasionally the strip will break or tear through this process, and when that happens, steel flies all over the place. So it's pretty well protected in this area here. So we don't have the ability to look at the strip while it's being reduced. It's all after the fact in this operation. Okay. Other questions about the tandem mill? Okay. We start the texturing process by putting a special texture or matte finish on the stand 5 rolls. It'll have a specific peak height and peak density on that roll. So that subsequent skin passing roll will put the actual mat on that your specifications require. But that process is started with the texturized roll here in stand 5. Okay. We had a question earlier about what kind of oils do we use at the pickler. I indicated that if it's coming to this facility here, we'll use a reduction lubricating oil. We will apply additional oil through the stands here to help the reduction process. At the end of the line here and on stand 5, we try to remove all of that residual lubrication with water and detergent. So in the first 4 stands, we're throwing lubrication on, and the 5th stand, we're trying to take it off. That lubrication carried downstream can cause problems with painting. It can cause problems with electrogalvanizing. So we want to remove it, put it on, and then take it off.
Do you keep track of the heats of this, doing batches of steels? What do you check?
Larry's question is, do we keep track of the batches of steel that go into the tandem mill? Okay. Yeah, we keep track of it through identification of each unique coil. Okay. In the steel making process, we have heats. Okay, and we keep track of that heat. But as soon as the heat is solidified, we now have slabs. And we identify that slab by a heat number and a slab number. As soon as that slab is rolled into a hot band, we have a hot band coil number. We keep track of that. As soon as that hot band is put into the pickler, we give it a coal mill coil number or a pickle coil number. Okay, we keep track of that. Pardon?
At that point, they're welded together.
Yes. Okay. If at the end of the pickler, and that's why we give it a unique number here, at the end of the pickling operation, we give it a unique pickle band number. Okay. It can have 1 hot band in it. It can have 5 hot bands in it. Regardless of what hot bands are in it, that's kept as part of its history. So if we had 3 hot bands in it, we could take a pickle number and look at what hot bands made it, what slabs, what heat, etc. So at each operation, we know the coil number coming in and we know the coil number coming out. Okay? That's how we keep track of that. Okay? So at the end of it, if you wanted to know, Larry, if you have a coil number, a coal mill coil number, I can tell you pretty darn quick the entire pedigree all the way through steel making. Okay, any other questions about the coal reduction process? If not, we'll go on to the next stage of the operation. When we tandem roll it, we're throwing a lot of energy into it. We're cold reducing it. We're taking a strip from the hot mill that's essentially soft, cold reducing it. That process makes it very hard through the cold working process. For instance, a typical drawing quality coal hot roll product will have a yield strength of, say, 32 KSI. Okay? Meaning it will take 32,000 pounds per square inch to deform the steel. We put that piece of steel into the coal mill, we reduce it 70%, we increase the strength to about 80 to 90 KSI. Okay? Just in that coal rolling process. We triple the strength. While we're tripling the strength, we're also removing its ability to stretch, or removing its ductility. So it's a real hard piece of steel, but it's basically useless. If you bend it much more than very generous 90-degree bends and roll form, it's going to break. You can't stretch it. You can't put in a draw die. It's got very few applications. So after we cold reduce it, we have to anneal it, soften it back up. Okay? The full hard product we'll send to our hot dip line, which has an anneal facility in front of it, a continuous anneal. And I'll talk about that, the continuous anneal technology here. But recognize that you'll also hear that when Dave Funk talks about the hot dip line. We can sell, and we do sell, a product called full hard. We'll sell a full hard product to people who have further processing, such as galvanizing lines or something with an anneal section in front of it. A lot of people process steel that way. Or for flat applications that don't have much bending, saw blades, for instance, will be purchased out of a full hard product. Strapping can be purchased out of a full hard product. But the majority of our steel goes through an anneal facility first. It's a very small amount of product is sold as full hard. Most of it goes to our anneal facilities. There's two methods to anneal. One is called the batch process. One is called the continuous process. To contrast the two right now, the continuous process is much the same as the pickler, where we pickle a single strip width. We attach one coil to the back of the other and pull it through and pickle a single strip width. That's the continuous anneal process. It just anneals the single strip width, decoils it. The batch process will anneal the entire coil at one time. Just take the whole coil, put it into a furnace, and heat it up. Okay? Let's talk about the batch process first. The batch process, before I talk about the batch process, let me talk a little bit more about the art of annealing, or the science, I should say. This is our metallurgy for the day, okay? So, class, pay attention. This is the good stuff here. This is about as technical as we'll get this morning. When we cold reduce steel, we elongate what's called the grain structure. Steel has got grains. It's built of grains. Just like a tree has got pulp. You've got cells in your skin. Steel is the same way. It's got cells or a molecular structure. It's crystalline. When you cold reduce that, you elongate those grains, and you make it very hard. Okay? There are a couple phases of anneal. One is the recovery stage. The recovery stage happens at low temperatures. Okay, that's the first stage of any anneal operation. Okay? And all it does is it removes some of the residual cold rolling stresses. Okay? And in this graphic, we've got a temperature chart, or excuse me, a crystalline chart, and we've got a ductility chart and a strength chart. Notice in this first operation of anneal called recovery, we start to get an increase of ductility without a loss of strength. This happens at about 1,000 degrees. We sell a product called stress relief anneal. 80,000 yield, 90,000 yield type products that go through nothing more than this very front end of the anneal cycle, where we remove some of the stresses to get a little bit more ductility out of it, but without any loss of strength. Okay? So if you hear the term stress relief anneal, that's all it is. Taken up to about 1,000 degrees. No real change in the crystalline structure, just some changes in the internal residual stresses to give yourself a little more stretchability or ductility without a loss of strength. As we climb the temperature range, we're going to take these elongated grains and they're going to do a phenomenon called recrystallize, where they're going to go from elongated grains to it's like a rebirth. They go back to a equiaxed round grain. Okay? This is the first stage of creating drawing quality steels. Okay? Notice that in the schematic of ductility and strength, through this process you have a dramatic increase in your formability or stretchability, but also the strength rapidly decreases. Okay? If you were going to buy a commercial quality steel, we anneal it just to recrystallize it. That's it. Okay? We get it to this stage right here, to recrystallized. If you're looking at adding to the ductility, we need a phenomenon called grain growth. And that occurs later on in the anneal cycle, through time. Recovery happens at about 1,000 degrees. Recrystallization happens at about 1,200 degrees, 1150 or 1,200. Grain growth happens greater at 1150 or hotter through time. Notice that while the grains are going from small equiax to big equiax, we don't have much of a change in hardness, but the ductility continues to rise. Our deep drawing quality or DQSK steels are in this range of the anneal cycle. Okay? So we recover, we recrystallize, we grow. That's the process of anneal. And depending upon which products you purchase, we'll produce them through the anneal cycles here. Now, there's some chemistry issues here too, but basically this is where we're making the strength issues. Okay? And those CQ, DQ, DQSK, EDDQ. Okay? It's important to know that. And this is time. Recrystallization in the batch anneal is 3 days. To get this grain growth, we're talking 5 and 6 days. Okay. So now you can start to appreciate some of the cost differences if you're into that end of the business between a DQ and a CQ and a DDQ. Yeah?
Could you throw that one back up there for a second? If the DQSK is out at the upper end of the ductility.
Before this, Tim is stretching the metallurgy class beyond 4.5 minutes. Do we want to allow him to do that? Go ahead, Tim.
DQSK is out at the upper end of the ductility. Where is the CQ then? Is that
the CQ would be right in here where we just get it to recrystallize so that we remove the full hard strength, okay? But that's it. It's a cost-efficient process to get something you can form. There's a lot of variability in it, but it gets rid of all the cold work that's built in through the cold reduction process, okay?
Is there another measurement of ductility between CQ and DQSK?
Commercially, we think there is, okay? In essence, you know, we're learning today that you basically have this product here, CQ. You've got a drawing quality product that's down in here, and you got a deep drawing quality product, okay? And sometimes the deep drawing quality products, we change the substrate to interstitial free steels and that sort of thing.
Is that another term they call DDQ plus? Where is that on the range?
It's over here. EDDQ, DDQ, DDQ plus, those are all commercial terms for things that are down in this range here, okay?
So giving you more ductility than the DQSK?
As we know DQSK, I mean, that's today with cast steels, everything is SK. Okay? SK means special killed or silicon killed, typically special killed. AK, aluminum killed. If it's continuous cast, it's all of that. But you can take an SK or an AK product and do the exact same thing and just kiss it on anneal and get a CQ product from it. Okay? So if we got to start to get away from those AK, SK terms and get down to the, is it a drawing quality or a deep drawing quality product? A CQ would be here, a DQ would be here, and a DDQ or an EDQ is way out here, okay? Or EDQ and DDQ, we can change the substrate to an interstitial free substrate and really manipulate this thing.
So Bill's looking to get away from the label of the CQ, CQS.
Try to put the label with it. I will say from a metallurgical standpoint, yeah, we're trying to move that way. There are commercial implications, which I don't understand, that are out there in running our business and how you sell your products and that sort of thing. Plus the nomenclature that a lot of our customers' purchasing agents have grown accustomed to and are used to. So it's still out there. But in reality, from a technical standpoint, a lot of that is unnecessary today. Okay. Just strictly from a technical standpoint, knowing what you're getting. What do you need and what are you getting? Okay, the batch anneal facility. In our batch anneal facility, as I said, we take a whole coil and anneal it. But we do more than that. We take a whole bunch of coils and anneal it. Okay? This is a pictorial of an anneal stack. In our batch anneal facility, as a quick description, we have stacks of coil up to 190 inches high, 4 of those stacks in a furnace. So anywhere up to typically 9 to 12 to 16 coils in a batch anneal heat. Okay? Hence the term batch anneal. You do a whole bunch at one time. And there's some economies of scale there. But when you go into the anneal facility, you'll see what looks like a bunch of small little grain silos. Those are nothing more than stacks of coils with covers on them. Inside the cover, you can see there would be 3, 4 coils stacked up on top of each other, sometimes 2 if they're real wide. At the bottom of the anneal stack is a pedestal with a fan in it. Between each coil, we have separator plates, which add a little air gap. Okay? The intent here is to circulate air through the eyes of the coil, down the aisles, out between, and then back up around the stack. So it's a continual flow of atmosphere around, heating the coil. Around that stack of coils, whether it be 2 high, 3 high, or 4 high, we put what's called an inner cover around it. And here's that grain silo looking device. Okay? Underneath this inner cover here is the stack of coils. Got the stack, we'll put the inner cover over it and seal the bottom. We'll then exchange the atmosphere, the air, for a hydrogen-nitrogen mix. The inner cover protects the coil with that atmosphere. We get the air out and put the hydrogen-nitrogen mix in because we're going to elevate the temperature of the coil. If we don't have the proper atmosphere surrounding the coils, you're going to oxidize the strip surface, just like you did slabs in the furnace, coils in the hot mill. Bring it up to temperature here. If it's a non-protective atmosphere, we're going to get stains, we're going to get oxide, it's going to look blue, it's going to be unacceptable. Okay? So we have to protect the coils with a protective atmosphere. We'll put 4 of these stacks on a base and put the outer cover down over those 4 stacks. The outer cover provides the heat. Okay? Natural gas fired will fire from the outer cover to the inner cover. We'll heat the inner cover. The inner cover heats the atmosphere is circulated around the coils. Okay? One of the problems we have with the batch anneal is that we're trying to heat up a massive piece of steel. Okay? It's kind of like barbecuing in your backyard. For those of you who barbecue chicken, you know that there's a delicate balance between getting the outer done and the inner done. Okay? Imagine a 20-ton piece of coil. How do you get the whole thing heated the same throughout without burning the edges or the outers? Very simple. You know, it's the same thing. It's hard to do. In fact, with some considering industrial efficiencies, we're always going to have a temperature gradient throughout that 20-ton hunk of steel. The outer is going to be hotter than the inner. That's one of the issues we have with batch annealing. Okay? We control batch anneal through the description of a couple temperatures. One is the hottest a coil can get. That's called the hot spot. The other temperature description is the cold spot, the minimum temperature that the coil must achieve, any part of the coil. Typically, batch anneal cycle might look like this: 1240 to 1340. You've got 12 coils in that batch anneal for heat. Each one of them is going to get over 1240 degrees, every spot of the coil. And none of the portions of the coil are ever going to exceed 1340. What that means is you can have 100 degrees difference in that coil from front to back. That difference creates some temperature gradients, which creates some mechanical property gradients. We can make this window smaller by turning the temperature of the fire down, just like the chicken. If your coals are hot, you're going to burn the outer surface and you're still going to have raw meat. Same thing here. We try to do the process too fast with a furnace temperature which is too hot, we're going to exceed that temperature and never meet that temperature. So the faster your anneal process goes, the larger this window's got to be. Hence, if you want to reduce the gradient of the batch anneal and create a smaller window, you're going to drive to a longer anneal cycle. So there's some efficiencies here, industrial efficiencies we've got to consider. We can reduce the window, but it's going to add tremendous time to that whole process.
If batch annealing isn't exact as your continuous heat treatment, why not put everything that needs annealing through continuous heat and forget about batch?
Okay. Tim asked the question, with those, to paraphrase, with those deficiencies, why do we batch anneal as opposed to continuous anneal? We'll get into that in a moment, okay? Because continuous anneal isn't free either, okay? As we'll discuss next. Just a couple things about the batch anneal facility. We can pile to 190 inches high. So depending upon your coil width, we can get 2, 3, 4 coils on top of each other. We have 63 bases. That's where we're putting the outer covers. Okay. We do have some single stack furnaces, meaning we can heat just one stack of steel as opposed to 4 stacks of steel. And we'll utilize those for some specialty cycles that we have, such as our high-strength cycles, so that you don't have to wait for 300 tons of steel to come along before you can anneal it. So for those cycles that don't have a lot of volume to it, we'll do a single stack as opposed to a 4 stack. And throughout the batch anneal facility, we use a rail car system to transport our steel. Okay. Now let's look at the continuous anneal process. The continuous anneal process decoils the strip, and we heat a single width or single thickness. Okay. This is our heat treat. First, I got to get this guy so that it looks correct on the screen. This is our heat treat process. It's a continuous process. We don't want it to stop through the facility. It's got a lot of the things that the pickler had on it. For that, it's got two decoilers so that you can weld one coil onto the next. First part of the continuous anneal process is a cleansing process. Remember I said that we tried to remove all of those rolling oils off the tandem mill? Well, we don't roll them all off. We don't clean them all off. So the first part of the process here is to clean it. Get the rest of those residuals off so that when you heat it up, you've got a clean strip. That's the first benefit of the continuous anneal technology. When you're batch annealing, you get a residue of the residual rolling solutions that are on the strip. When they're heated up, they create a carbonaceous type residue. You can wipe your hand on a batch anneal coil and it'll kind of darkish, smutty. Since we're cleaning this before we anneal it, we don't have that smut issue. We decoil it, we put it through an accumulator, we heat it up through a preheat section, a heat section, and then we soak the little guy. When we soak it, this is the first key temperature. We don't talk about a window here, we talk about a temperature. Depending upon the cycle, the controlling temperature might be 1,300 degrees. Remember in the batch, we said 1,240 to 1,340? Here it's 1,300 degrees. There is a tolerance around that built within the process control, but it's not a 100-degree tolerance, it's about a 30-degree tolerance. Okay? So you heat it up, a single strip up to 1,300 degrees or 1,500, depending upon what kind of product you're trying to build. Then you rapidly cool it down and quench it. If we're building high-strength steels, we'll take advantage of this process here and manipulate the cooling rate so that we can build extra strength. This is how we build dual-phase products. We'll heat it up, and then we'll throw it in a quench and rapidly cool it. Then we clean it again. And we heat it up again. Why do we heat it up again? This is another metallurgy class here. We heat it up again because we have to allow the carbon, which is in the steel, to diffuse to preferred site. Okay? When we rapidly cool steel from a soak temperature, we're locking carbon into what's called solid solution. It's just like salt water. When it's hot, you can dissolve a lot of salt in the water, more than you can when it's cold. Okay? So when you got a supersaturated hot solution and cool it down real rapidly, you don't precipitate the salt out in the salt water. It gets locked into solution. Same thing with steel and carbon. The carbon doesn't want to be in solution, yet it's locked there because you cooled it so fast. If you don't heat it up later on, when the product is, the carbon is going to move around on itself through time and age the steel. We've heard about aging when we talked about rim steels and old steels in the past, where the steel mill would ship it and it gets harder over time. If we didn't heat it up here, the same thing would happen. Okay? So we got to heat it up in this overage section, or we'll age the steel will age later on and create a thing called strain lines when you go to form it, which is unacceptable. Heat it up to about 700 degrees. Cool it back down. Accumulate it, tension level it, and coil it. Okay? Now, before we answer Tim's question here, we're going to go to this chart here. Let's compare now in time continuous anneal and batch anneal. Both anneal processes, whether it be continuous or batch anneal, take the steel up to a specified temperature, a metallurgical temperature called A1. It's the critical temperature. You got to get it above there. With batch anneal, we said earlier, for a CQ product, it takes about 3 days. Okay? And in the continuous anneal, it'll take about 8 minutes. Let's go back to the metallurgical chart I showed earlier that had grain size, residual stresses, ductility, and strength on it. Remember way over here on the right side of that graph, it said grain growth was the key to drawing quality products. You don't get grain growth in 8 minutes. Remember we said CQ just got us to recrystallization, and then you allow it to stay in there for a couple more days and you got grain growth. Big disadvantage with a continuous anneal process. Because it's so short, you don't have the ability to grow the grains. Therefore, with the conventional carbon substrate, with no alloys in it, you have a difficult time making something that's going to form into today's panels. Big disadvantage. We can get over that hurdle by going to interstitial-free substrates. Okay? With an interstitial-free substrate, you can produce an extra deep drawing quality product off of CHTL. But you're going to be paying for it through the cost of the liquid of the steel making process. Because you're going to be degassing the steel, you're going to be throwing in titanium and or columbium, a lot of different other processes. Okay? So, Tim, you don't want to use continuous anneal for deep drawing quality products on conventional substrates because you're not going to get the drawing quality out of it. You can use it and get the drawing quality out of it with interstitial-free substrates, but there's cost penalties involved. Okay, does that help answer that question? Now, the hot dip line has a continuous anneal line in front of it. So, if we're going to get drawing quality products out of the hot dip line, we need to use interstitial-free steels in front of it. Okay. As you're purchasing steel from continuous hot dip lines, that's the way they're run. The drawing quality products there are built with interstitial-free steels. Okay. So you'll see typically a more formable product coming off of a continuous anneal hot dip line than you will. It'll be a little more formable than a drawing quality or deep drawing cold roll substrate or electric galvanized product. Okay? Simply because that technology requires interstitial free steels. Questions about batch annealing or continuous annealing? Yes, sir.
You just quickly threw out something about the hot dip coating line. And I'm glad you threw that up there because from the tandem mill, we can go for the two you just described, continuous heat treating, annealing, and batch annealing. Take the tandem mill and drop straight down, and that's the hot dip coating line.
Yes.
Are you about to talk about that, or are we done with that?
Dave Funk will talk about that. When I'm finished here, Dave will talk about hot dip coating line and our electric galvanized coating line, okay? And as we say, that's got an anneal facility right in the front of it. It's the continuous anneal technology. Okay, other questions about annealing? Yeah?
From a product mix, high strength versus the regular cold rolled items, would most of the high strength be done on the continuous anneal?
Yes. At Burns Harbor, for this facility, we'll produce, if the size permits, produce our B40s and B50s on the continuous anneal line. Okay, it does have some size limitations, thickness and width. 58 wide, 060 thick. Okay, if it's less than those two, we'll produce it on the continuous anneal line. Okay, it's a natural fit.
I have a question. Used to metal would get an age mark. Yes. Anymore, it doesn't do that.
Correct.
Is that where you get your growth on your metal?
No, the aging phenomena comes with carbon or nitrogen floating around in the steel. Okay? With aluminum-killed steels of today, or with overage in continuous anneal, the carbon and the nitrogen are pretty tied up, so they're happy where they're at after the anneal process. Okay? It's got nothing to do with grain growth. It's just those elements and their state inside the steel. Yes. Is there another question on anneal?
On anneal, DQ and DQSKs and the IFs.
Yes.
Would that typically be just out of batch anneal product?
The DQSK, or the deep drawing quality, that's non-IF, would come from a batch anneal process. A deep drawing quality that is interstitial free can come from either or. Depending upon how you want to define drawing quality, we can produce that on the continuous anneal line. Let's throw Rockwell. I don't like to use Rockwell when we're talking about forming characteristics, but it's a good relative measurement. Okay? If you take a 3-carbon steel with a little manganese in it and put it through a continuous anneal line, your Rockwell is going to be around 50 to 55. Okay? If you take that same steel and put it in batch anneal, your Rockwell is going to be between 40 and 45. Okay? Now, how you define drawing quality, or what your need is, will really dictate whether that 50 to 55 Rockwell off of a continuous anneal line is your drawing quality. Okay? It can do some things. We can form it. We can stretch it. We can draw it moderately. If that's a drawing quality product, yeah, we can do it on the continuous anneal line. But a deep drawing or a DQSK nomenclature, no. Okay. Jim, does that answer?
Yes, sure.
Provided? Okay. After the anneal, we send the product to our temper mill, skin mill, dual mill. It's a coal reduction mill. The purpose is to harden the steel up. God, that's kind of contrary to what we just did in anneal. In anneal, we softened it. Now we got to harden it. Okay. But not only do we restore the proper hardness through the tempering process, we also improve the flatness a little bit. Through the anneal, you get some distortions. We don't remove those. And we provide the matte finish that's required, okay, for exposed applications. We do that through texturizing, through blasting or electron discharge texturing, EDT. We put a surface on the work rolls that's going to be imprinted on the steel itself. Okay. Now, let's discuss a little bit improve the hardness or restore the hardness. Through anneal, in the dead soft condition, steel products have, except for interstitial free steels, the conventional substrates have what's called a yield point in them. We can remove that yield point. It's a metallurgical thing, just accept it, okay? We remove that yield point by cold reducing, small amounts. 0.5% is typically sufficient. If we don't remove that metallurgical thing called the yield point, when you form the product, you're going to get strain lines or orange peel or Luder's lines on the product. Most of us have seen those kind of things. They're ugly. They're unacceptable for exposed applications. You've got to remove that if you're going to put it into some sort of a forming operation and expect it to look good. It's basically what restoring the proper hardness means. Removing that metallurgical yield point or phenomena. And we do that through the cold reduction process. The skin mill is nothing more than a single stand reduction mill, just like the tandem mill, just like in the hot mill. 2 backup rolls, 2 work rolls, a single coil gets decoiled through the mill. We monitor the elongation that we give it. We monitor the gauge. We crop the ends. We've got a finished coil. Okay? Typically a 0.5% reduction, up to 1.5, depending upon the specification of the product that we're producing. Okay? At the tandem mill was a non-continuous process. It started and it stopped. The gauge control as you start in the tandem mill is not as good as through the body, and as you stop is not as good through the body because you're accelerating and decelerating and predicting roll forces and all that stuff. We'll crop those ends off here in this process. We'll crop the outer laps to get us into body gauge, and then we'll stop the coil and remove the inner or the start of the tandem mill process here. So when the coil is temper mill rolled, it's got the off gauge ends removed, the off gauge from the previous operation. Any questions about the skin pass operation? I will add that we do inspect the product here. We have a booth at this end of the mill where the inspector looks in at the strip, looking for roll marks, looking for scale, looking for all those imperfections that can be there. We also take a sample of every coil. We look at that sample, we measure it, width, thickness-wise, and if required by the specification, we'll send that sample to our laboratory for mechanical testing. Okay. Essentially, for most applications, the coil's done. That's it. We'll package it and ship it. Yeah, Tim.
You got an inspector there. Is it just a visual inspection as this thing is flying by?
Yeah.
And if that's true, how much can you really see? And
Okay.
what can you stop once you see it?
Excellent point. And the strip is traveling about 4,000 foot per minute. What can the guy really see? Okay, we do have some enhancements there which allow him to see some things. But for real critical nature products, hoods, things of that nature that are going to get scrutinized to a high degree later on, we find that an additional inspection process is necessary at slower speeds where you can stop the coil and look at it. Okay? So if it's of a critical surface nature, we may elect to take this coil and put it to a standalone inspection unit. For a large majority of our products, it's shippable right there. Unexposed, certainly. Okay? Some non-critical surface application, non-critical yet exposed, we can ship it right there. There's another question.
How does overgauge or undergauge on the head end or tail end escape after this process?
Okay.
Because we seem to see that.
Yeah. The question is, how does off gauge escape? Human error. It's strictly that. And let me explain this to you. We have off gauge on the head and tail from the tandem mill. We have installed an X-ray gauge right here in the preparation area so that we delap until that X-ray gauge shows that you've got in-body gauge. We have at the roller's pulpit a message from the tandem mill that says on this end of the coil, on the inner end, you have so many feet of off gauge. So he's going to stop the coil before it gets there. Here we have an X-ray gauge. This X-ray gauge looks at the coil from the front to the back, and it displays the reading on a screen in front of the inspector. So the inspector can see front to back the gauge profile. When all of that works and a coil gets out, it's a human issue. I have no other way to explain it. Over the past several years, we've provided these additional tools to help eliminate those kind of conditions getting out. And still they do. That's an execution, strictly a human execution type thing.
Like do the audit with a hand mic, just
Yeah. Do we do a hand audit? Yes, we do. Remember I said we take a sample here at the end, and one of the things that we do, we put a tape measure to measure the width, and we measure the thickness with a micrometer. This X-ray gauge here is a center width gauge. Okay? So the inspector measures the edge to make certain that our crown, the difference between the edge and the center, is within our statistical prediction. Okay? So there's a checking there. Did I answer? Did I help answer your question? I mean, it's an embarrassing thing. It truly is.
Well, that specific application that we buy that for is a gauge critical. That's why I really don't understand why it's still
Embarrassing. 4 years ago, we didn't have the display screens here which say what it is front to back, and we didn't have the X-rays here, but we put all that in to help eliminate those things from getting out. Yet occasionally they do.
Over the years. Almost never. Still occurs.
Other questions on the skin mill? Okay. If I'm going to skipping through a bunch of pages here. Occasionally after skin pass, we do need additional processing. We might need additional processing if it's a critical surface product and our inspection at 4,000 feet per minute off the skin mill is not acceptable for that standard. It might require further processing if we have an exacting width tolerance, which requires us to trim the product to width after all the processing. Remember, if we don't have that exacting tolerance, we'll do that operation at the pickler. Okay? So if we have exacting tolerances, we'll trim it after. We might find an imperfection that needs to be removed, such as after the skin mill practice, if the inspector says, hey, we still have some off gauge here that needs to be removed. Or, hey, I saw a roll mark. Or, hey, I saw a pincher. We got to remove these things. He would send the product to a finishing facility to remove that imperfection. Okay? So for those purposes, we have a rewind line, we have two slitters. And basically, they decoil. They allow us to look at products slow. They allow us to trim it to width. They allow us to cut things out. Okay? We can send the coil to our Walbridge electric galvanizing facility. This is in Walbridge, Ohio. We have discontinued operation of our Burns Harbor electric galvanized line. When you tour the coal mill facility, you'll see an old electric galvanizing line just sitting there. It's 48 inches wide. The technology of that line could no longer support our electric galvanized business. The products that we're selling for electric galvanized today require good, perfect surfaces. The technology of that line could not deliver the surfaces required. And the other business available was not sufficient enough to keep it going. So we've shut this down. It's been down a year and a half now. And we have a cold roll shear. That cuts rectangles. We eliminated that from our process also. Same time we took the the electric galvanized line down. We took the shear down. We didn't have enough business to support that operation. Okay. Rectangular shears are going by the wayside. Most people who are using blanks these days are using configured blanks. So that business for rectangles is just not there. Some of our warehouses that we sell to, or processors that we sell to, are much better at that than we are. Okay, yeah, Tim.
Obviously, GM buying a lot of configured blanks, so basically from Burns Harbor here, you're getting the coils, and then you're sending them out to a processor?
Yes.
And then they're cutting the blanks for us?
Yes.
Are there any particular processors that Bethlehem is teamed up with on the majority of their work?
Okay. We do not have, for blanking, we don't have strategic partnerships. When I say strategic, monetary partnerships. But we do have processors which we feel do a better job than other processors, and we send our business their way. In fact, we'll do a single bill invoicing for you, so that basically you buy the blank from us, and in turn the coil to them. They'll do the configured blank, and we'll sell you a number of pieces on a single bill. Okay. I hope that I've done a good job describing the coal mill for you. You're going to go out and see that later this morning. Dave is going to follow up and talk about the hot dip line and the electric galvanized process. We've got another couple minutes here. Are there any additional questions that you have that I might be able to answer for you? Yeah, Chuck.
I missed about the dual line. What is that? What do you do with that?
Yeah, I intentionally went by that one without mentioning it. The dual mill. The dual mill is a coal reduction mill, just like the skin mill, only it's got 2 mill housings. Okay? It's narrow. It's meant to provide greater reductions than the single stand skin mill. When this plant was built, one of the products that we sold was tin plate product, very thin, 012 thick. We used the skin mill, or the dual mill, to do the coal reduction for that product. Okay? Many years ago, we got out of the tin plate business. Therefore, the dual mill just became a regular coal reduction facility to do the same work that the skin mill does. Last year, we basically shut the dual mill down because we now have a product mix with our hot dip line, taking a lot of our cold reduced material and sending it that way. We don't need the skin pass capacity anymore that two mills gives us, a dual mill and a skin mill. So we were running the skin mill basically 12 turns a week and the dual mill 5 turns a week. At the end of last year, we shut the dual mill down, and now we've increased the skin mill turns to 18, 19 turns a week. Okay? So I intentionally skipped by because we don't use it anymore. We don't plan on using it unless we have some shift in our business patterns. And I don't foresee that for some time. Any other questions? Yeah, Tim.
The electro galvanized, obviously you said you don't do it here anymore. It goes to the Walbridge, Ohio facility.
Yes.
What kind of tonnage are we talking about?
Off of Walbridge, that is a joint venture. There are 3 partners in that: Bethlehem Steel, Inland Steel, and Pre-Finished Metals. Pre-Finished Metals, it's basically their equipment, and they manage it. We own 75%, Bethlehem owns 75% of that capacity. That's about 32,000 ton a month for Bethlehem. Okay.
Is there a large demand for electro-galvanized coils?
Yes. In fact, for the last 2 years, we have been unable to provide our entire electric galvanized order book through Walbridge. We've had to contract out. In fact, one of your big parts, the CK pickup truck door panel that's going to Indianapolis, we've been coating that for the last 2 years at LS2, which is an LTV coating venture. Okay, so we do have, for the last 2 years, we've had more tonnage than that facility can handle.
So if there's the demand for this electrogalvanized, is there any talk of restarting the electrogalvanized here at Burns Harbor?
No. One, there's two reasons that we're not entertaining that. One is the technology of that line cannot support the quality of the applications which we're selling to. Okay, it's really, you can't do doors on it, you can't do hoods on it, you can't do deck lids on it, and that's the business. Okay, you can't do them because there's too many surface imperfections that are inherent in that design. Okay. Second reason is that the future of electrogalvanized is going to be diminished as the technology of our hot dip process allows us to start producing a lot of the qualities, surface qualities, that heretofore have been the domain of electrogalvanizing. Okay? So we're seeing shifts to hot dip products away from electrogalvanized products. Okay? So we don't foresee that. Okay, if there are no more questions, we're going to allow you to take a very short break, and then Dave is going to be here to discuss the coating operations.
All right, good morning. My name is Dave Funk. I work in the coal mill in the quality assurance group with Pete Hollingsworth, who just talked to you this morning. And I'm going to switch gears a little bit and start talking about hot dip galvanized, hot dip galvanneal, and electro galvanized. If you have any questions at all at any time, just shout them out or raise your hand, whatever. Again, we're going to talk about coated products. I'm going to start off just talking about corrosion protection in general, why you would want it, what's the purpose of it, how it works. Kind of go into two different types of hot dip coatings that are available from Burns Harbor, actually for most people, that being galvanized and galvanneal. Most people are probably familiar with galvanized. Some of you may not be that familiar with galvanneal. Talk about hot dip lines in general, and more specifically how ours works here at Burns Harbor, and kind of compare that with a line that we have outside of Buffalo, New York, a place called Lackawanna, which through marvels of bookkeeping is actually part of this plant. So compare, that's an older line, compare that to a newer line, some of the technologies and advantages of each line. Then we're going to shift gears and start talking about electro-galvanized, talk about the process there, how that works, and then talk about the electro-galvanized line that we have outside of Toledo at a place called Walbridge, Ohio, and go through kind of that line and how it works. So again, if you have any questions at all, shout them out. Let's talk about corrosion protection in general. Probably not giving away any trade secrets. Maybe I should turn off the mic, but steel does rust sometimes. We want to, of course, get around that. That's why we're talking about corrosion protection. There's basically three major categories or three major ways you can accomplish that. The first one, very simple, called the primary barrier. Basically, it's paint, something like that. If you had a filing cabinet, you paint it, you let it sit in your office for 20 years, it's probably not going to rust. As long as that coating stays intact, it's going to be okay. Of course, if you get a scratch in it and you pour water on it and salt and all that kind of stuff, it's going to start rusting out. So for a filing cabinet, it may be okay. For your car fender, it probably isn't, because you know it's going to get scratched, so you know it's going to get exposed to salt and moisture and heat and all that. So some advantages to it. It's cheap and it works rather well, but not in a in a harsh environment. So that would be the first and simplest kind of corrosion protection. The second one, what we call sacrificial type protection, those are the zinc type coatings, and that's what we're going to talk about today, where the coating itself actually sacrifices itself to help protect the base metal through a mechanism, and we'll show that on the next slide, how that mechanism actually works. But the important thing is that the coating is sacrificing itself. It's an active mechanism. It's not just a paint barrier or a layer of zinc. It's actually doing something while it's there. So we'll talk about that in more detail. And the third one, just to kind of be complete, what they call a barrier type protection. And here you're talking about aluminum type coatings or zinc aluminum type coatings, where the aluminum is actually forming a tough aluminum oxide coating to help protect the base metal. Very good for corrosion protection. has other disadvantages as far as painting and welding and stuff, but very good for corrosion protection also. So those are your three basic types. And again, the sacrificial is what we're going to concentrate on. Just to kind of illustrate that primary barrier again, as long as the coating stays intact, you won't have rust. Of course, you get a scratch on your fender, it's going to start rusting out. In no time at all, you have a big hole in the side of your car. So trying to get away from that, with the zinc type coatings, the sacrificial coatings, it does act as a primary barrier, protects the base metal from exposure to moisture or air, does that very well. The intriguing part about the zinc is when it does get a scratch in it, is that it'll actually try to heal over that scratch through galvanic action, kind of a little battery galvanic cell, hence galvanized coatings, will try to heal over that scratch. There's actually electrons flowing back and forth with different electromotive potentials and all that. But the important thing is that the zinc will try to fill in that to get all the electrons happy again. So that's the advantage of zinc, is that it's actually going to try to heal over a scratch, not just protect it from rusting in the first place as a primary barrier, but if you do have a breach in the coating, it'll try to heal it over. And that's why it works so well, because sooner or later your car is going to get scratched. Just to kind of illustrate this in a different way, these are samples that were subjected to a salt spray test. In this case, these were cold rolled samples that were painted. Then a scribe mark or a scratch was put on it to scratch through the coating. Then they put them into a little cell where they elevate the temperatures, humidity, throw some salt in there, things like that to kind of accelerate a normal wear out on the road or the highway. And of course, as you would expect, the painted sample just rusted out. Now on the galvanized side, these are actually electrogalvanized samples, but electrogalvanized and hot dip, the zinc works the same way. Zinc is zinc. It doesn't know how it was put on. But these are cold roll samples that were electrogalvanized and then painted and then scratched all the way down to the base metal, and you can see that they didn't rust out. The coating kind of healed itself and helped protect that. Of course, the scratch doesn't go away, but it doesn't rust out. And just to illustrate in a little different way, that one slide where I showed you how the zinc worked, the more zinc you have available to heal over that scratch, the better it will be at doing it. Or if the scratch is smaller, the better it will be at doing it. So you have a bigger scratch and not a lot of zinc, you may be out of luck. So just to kind of show you that the more zinc you have, the better corrosion protection you have. And also on here, I talked about those barrier type protections, the aluminum coatings. You can see what a good job they do as far as corrosion resistance at a lesser coating weight. You get very good corrosion resistance. This product here is called Galvalume. We make it down at our Sparrows Point plant outside Baltimore. It's about 55% aluminum, the rest being zinc. Very good corrosion protection, kind of tough to paint and weld and stuff, but for guardrails, things like that, a very good product. Will last out there for years and years. So again, just kind of illustrate different points here. Okay, let's talk about some coatings themselves. I mentioned that we produce 2 coatings here at Burns Harbor on our hot dip line, and actually at Lackawanna also, that being galvanized and galvanneal. Galvanized, pretty much basic, let me get some samples here. What people are used to, garbage cans, things like that. You see nice shiny zinc surface, lots of spangle, as it's called. It's, oh, that's a galvanized bucket or a galvanized garbage can or galvanized nails or whatever. Kind of a thick, heavy coating on that one. This was actually from our Lackawanna sample, or Lackawanna line. We don't produce a sample like that. That's a spangled product. Some people want that. People are making grain silos and buckets and stuff. It's a nice, easy way to make it, and people know it's got zinc on it because it's got that spangle look to it. Of course, most people wouldn't want a car fender looking like that. But so we have a non-spangled process here. Again, that was made at Lackawanna. The way that you make a spangled product is you would have a little bit of zinc, a little bit of lead or a little bit of antimony, something like that, in your pot. And when the molten zinc goes on the strip, when it cools, the little atoms of lead or antimony form a nucleation site for those crystals to grow. So if you have a little atom of lead there, a little crystal will start growing around it when the zinc cools, and hence you get that spangled look. So if you want that, that's how you do that. And that's the way most people used to do it. You know, for 100 years, people have been galvanizing steel. And most of the zinc that comes out of the ground has lead in it, so that's just the way you got it. Now people, of course, a lot of people don't want that spangled look, so the zinc that we put into our bath is a lead-free zinc. So we don't have a site for that nucleation to start, so we don't get the spangle growth on it. I have a sample. This is actually a sample of our Burns Harbor product here, and another one of the Lackawanna. Watch out on some of the edges of these, they're a little bit sharp. But, and you can see the Lackawanna sample doesn't have the spangle anymore. About 2 or 3 years ago, they went to a no-lead pot also. So they no longer produce that type of product, but it's nice to have because that's a good starting point to understand zinc. But as you'll see when the samples come around, it's a nice smooth coating now. It doesn't have the spangled look. These are temper rolls, so they have a nice smooth texture to them. Actually, when it comes out of the pot, and you'll probably see it on your tour today, the hot dip line, it almost has a mirror-like surface to it when the zinc is first applied to it. It's nice and shiny and smooth, smooth coating. We actually have to rough it up at the temper mill on the hot dip line in order to kind of give you something for paint to stick to and stuff. Otherwise, it'd be too smooth to paint. I mean, it looks like a mirror. So that's how we got away from the spangled coatings that most people are familiar with. And that's what most people do on a hot dip line nowadays anyway. Unless they're producing specifically for trade that wants a spangled product, a lot of the newer lines coming on are spangle-free lines. Okay, the coating itself, here would be your steel coming down here. When it goes through the hot dip line, our steel is heated up to about 860 degrees because it's coming out of an annealing furnace, and we'll show you that when we go through the line. But the steel is about 860 degrees. The molten zinc is about 860 degrees. So you got a fair amount of heat there. From here on out is where the zinc's going to hit the steel. And when they hit each other, or when the zinc is applied to the steel, the iron that's in the steel will actually start to migrate up through the coating, forming an alloy layer there. So that's kind of how the zinc is held on, as opposed to electrogalvanized, where it's electrolytic process. You're kind of just dumping it one on top of the other, and the iron that comes through kind of helps hold it a little bit. So you have this zinc iron alloy here, but the important part about galvanized is that you still have pure zinc on the surface. That's why you still have that nice shiny zinc surface to it. But this is important to know just as far as adhesions and stuff, what's going on underneath the coating. But this is in hot dip galvanized. This is the part that you're interested in. Now we get a little bit more exotic and talk about galvanneal. Galvanneal is a different type of coating. It's actually a zinc coating. It just looks a little bit different. You can see it has a dull gray surface to it. It's basically started off as a galvanized sample. When it came out of the zinc pot, it looked just the same as those other samples going around. What we've done, let me pass these two around while I'm talking here. What we've done is, here's your base metal steel going through the line. There's where your zinc was that was that was stuck on the steel when it went through the zinc bath. That little bit of alloy growth happened just like it did on the last slide that I showed, basically to form the galvanized. Before that could solidify, while you still had molten zinc on there, what we do is heat it up to about 1025 degrees for maybe only about 10 seconds and allow that alloy growth to continue all the way to the surface. So what we're doing is kind of that little alloy layer that was making the zinc stick to the steel, we actually just kept that growing. So it went all the way to the surface. And on galvanneal, you no longer have any pure zinc on the surface. It's all this zinc iron alloy, and hence it has this dull gray look to it. It looks almost like a cold rolled surface because it actually has iron on the surface. It's not just zinc there. You can see, not very much when you get right to the very top surface, but throughout it you have an average of about 10% in the coating. So about 10% iron is enough to give it that kind of a look to it. And that's kind of interesting, but why would anybody want to do that? I mean, you want zinc for your corrosion protection, that should be about it. Some interesting properties of this, it gives you a better weldability than the regular galvanized. In the regular galvanized, basically you got to get through all that zinc before you can weld anything, until you get to the steel to weld. Here you already have some iron in the coating, makes it a little bit easier to weld it, so your welding tip life is extended. The other advantage of it is, you see, hopefully by the time you get the galvanized ones, you'll see how smooth that is. Sometimes painting galvanized doesn't really go so well. With the galvanneal, the surface is a lot more porous, allows the paint to stick a lot better. So you have a better paintability and a better weldability because it's getting closer to a cold rolled surface there. It's more what people are used to when they're painting and welding steel. So it has those two advantages of paintability and weldability. Well, it sounds, why wouldn't everybody want that then? It doesn't really cost a lot more. All you're doing is heating it up. The major disadvantage is the powdering problems with galvanneal. Now on the galvanized, there was just a little bit of an alloy layer in here. On the galvanneal, since we allowed that to go all the way to the surface, close to the interface here, you have an alloy. It's a very high iron content. This is a very brittle alloy. It's not very strong. So when you go and bend this piece and form it or whatever you're going to do to it, sometimes you can have some powdering where it'll start flaking off right here. And your coating will start flaking off. So if you have a severe bend or a severe draw, you may start getting some of this coating flaking off because now you have an alloy that's kind of brittle. Whereas in galvanized, you can bend it all day long and for the most part it's not going to come off. So there's a drawback to it. If you've got something that's a big draw or high forming part, probably this isn't the way you want to go. If you got something that's a fairly easy draw but you need weldability, you need paintability, maybe this is the way to go. So there's advantages and disadvantages of either one. Let's talk about the hot dip line at Burns Harbor here. Yes?
From a corrosion standpoint, what would be the advantage?
They're both about the same. Now, if you go, say you had to compare the same coating weight. So if you have 60 grams on one side, or 60 grams per square meter of a galvanized, and 60 grams per square meter of a galvanneal, now that 60 grams, kind of 10% of that's going to be iron. So you may only have, 54 or whatever it turns out to be percent zinc. That's not a lot of difference. For the most part, they're pretty much the same as far as corrosion protection. Slightly better maybe on the galvanized, but 60 grams are just about the same. Anything else on that? Nope. Okay, let's talk about our hot dip line here at Burns Harbor. The line here is, we still consider it fairly new. It was started up in December of '92, so it's a couple years old now, but we still think of it as a new line. We start off with full hard coils from the tandem mill. Pete kind of walked you through the cold mill processing this morning, from the pickler to the tandem mill, and then if it was a cold roll product, it would go to batch anneal or continuous anneal, temper mills, and all that kind of stuff. Well, we get it straight from the tandem mill, and you'll see that on your tour. When you go, you'll start off at the end of the pickle line, then go to the tandem mill, and then right around the corner is the hot dip line. So it's actually positioned where it should be, which is a marvel of engineering in itself. The things are actually laid out in a logical sequence. So we would start with two payoff reels at the entry end. This is a continuous line, just as Pete kind of talked you through the pickler and the CHTL, how they were continuous lines. So you had the tail end of one coil and the head end of the other coil being welded together. This is no different than that, and no different than any other continuous line you'll see, where you have an entry tower and a delivery tower. The center part of the line should run all the time. Constant speeds, temperatures, pressures. You always want this part of the line to run in order to produce a good product. And the reason you have the entry and delivery towers is so you can shut down this end of the line to make a weld for the next coil, and you can shut down this end of the line in order to take a coil off or do whatever you have to do with that end. The important part is this part's always running. So you put the tail end, or start feeding up the head end of the next coil. There's an entry end thickness gauge that's going to measure the gauge of the coil coming in. And this line is all computerized, modern line, of course. It knows what the order should be, and it'll chop off the excess gauge till it gets on gauge. Part of the problem with that is the tandem mill, and I assume Pete kind of talked a little bit about this. The tandem mill is not a continuous line. You put a coil in, and then you run it through and you take it off. The heads and tail ends of a coil off the tandem mill sometimes are a little heavy gauge because it's not up to speed yet, it's not up to pressures and all that kind of stuff. So we kind of have it set. I keep worrying about tripping over this thing. We kind of have it set so it'll chop off as much scrap as needed until it gets on gauge. So if it's 20 foot of scrap, chops it off, it sees it's on gauge, goes to weld it up. If it's 100 foot of scrap, just keeps chopping until it's on gauge. So we shouldn't have any problem with off-gauge product on the hot dip line because of the tandem mill ends. So we should take care of that. And it does the same thing on the tail end also. So they'll weld it up together. So now you got a weld going through. Goes through a little bit of a pre-cleaner, knock off some of the tandem mill oils and fines. Goes through the entry tower. Comes up to our cleaning section. We have what we think is a very good cleaning section, probably one of the better ones around. Has electromagnetic scrubbers and magnets and all that kind of stuff, and good cleaning solution in order to get a good clean strip. In hot dip galvanized, or actually in electro galvanized, anytime you want to put something on the steel, you got to have it very clean. So we have a very good cleaning system, with scrubber brushes, magnetic separators, things like that, in order to get a clean surface. You want it clean before you anneal it, in order so you get a good anneal, and then you want it clean when you coat it in order so the zinc can stick to it. So there's two reasons to get a good clean strip. So we clean it here, then it'll go into our annealing furnace, kind of similar to the one that you talked about this morning a little bit on our CHTL, in that it's a reducing atmosphere, runs about 4% hydrogen, the rest is nitrogen. It goes into the preheat section, which will heat it up to about 350 degrees, just to kind of get things going and loosened up, keep the tension straight. Then it'll go into a heat section, where it's going to heat it up to the temperature it's desired to get the properties that we want. And that could be anywhere from about 1300 degrees to about 1550 degrees, depending again on the steel grade and what we want out of it when we're finally done. Then it'll go into a soak section, which will basically hold it at that same temperature for just a little bit of time. It's only 30 seconds. The whole time in the furnace here is probably only about a minute and a half. So when I say soak, it's not holding it there for an hour. It's only holding it for about 30 seconds. But that's enough kind of to let the properties sink in at that temperature. Then we go into a cooling section, what we call the combo cool. Because if you remember, I mentioned when it gets into the zinc pot, it's got to be about 860 degrees. You don't want to put a 1500 degree strip into 800 degree zinc, and it'll start bubbling away on you. So this actually cools it down in a controlled cool fashion until it gets to the zinc pot. Let me kind of blow up that area of the line here, because that's kind of the heart of the line. It'll come out of the annealing furnace, out of that cooled area. It's about 860 degrees now. And the exit end of the furnace is actually under the level of the zinc. When you go out on your tour, you just see this big piece of metal coming down into the zinc. The strip is actually in that, what we call the snout, because you don't want it exposed to any air or moisture. Now it's a clean strip. It's an active strip because it's heated up to 860 degrees. If you had a little bit of air or moisture in there, boy, that would suck it right up and you'd have rust like that. So you want to make sure it doesn't get exposed to any air or moisture, so it comes underneath the surface of the zinc, so nothing can get at the strip. Come down through the pot around the sink roll. This whole pot will hold about 200 tons of zinc, and you'll see the size of it on your tour. So it goes down, comes back up through a correcting and stabilizing roll just to kind of get the pass line straight, keep the tension straight, and then it'll come out of the zinc. At this point, the zinc is pretty viscous. It's kind of looks like molasses or syrup or something like that. It's very thick, viscous material. So when the strip comes out, it's going to pull up a lot more zinc than you want on the strip. And it's not going to be very smooth. It's just kind of pulling up whatever comes up with it. The trick with hot dip galvanizing is try to create the coating, of course, that the customer wants. So if you ordered 60 grams per square meter, we want to give you 60 grams per square meter. And we want it to look nice across the surface. So we have to blow off the excess zinc. And we do that with what we call air knives, or we happen to use nitrogen most of the time. Some people use air, some people use steam, some people use nitrogen. They all pretty much do the same thing, which is to blow off the excess zinc so you get a nice clean strip going all the way across at the proper coating weight. The way we control that, you can go back to this big, the big view here. This is where we were just looking at the zinc pot here. This is the air knives that are blowing off the zinc. That's controlled by a coating weight gauge that's on the top of the tower. If you're driving around your tour yesterday, you notice the big, huge building over here on this end of the mill. That's the hot dip line. That's the coating tower. It's about, I don't know, 13 stories high, tallest building in Porter County. So that's the X-ray gauge on top, and there's actually two X-ray gauges, one for the top of the strip and one for the bottom of the strip. And those gauges are scanning back and forth across the strip measuring the coating weight across the width of the strip, and as the strip is running, of course, across the length of the strip. And those are tied in. This one, the one on top will be tied into that air knife, the one on bottom will be tied into that one to control the coating weight. So say your aim is 60 grams per square meter, the gauge up here is reading 66 grams. It's going to say, hey, blow a little harder, get that down a little bit. And it'll automatically adjust the air knives and blow a little harder. And then I'll come up here and say, okay, I'm at 60 now, I'm happy, keep it like that. And the same thing, if it read a little bit lower, it would say blow a little bit less. Or it could also tell it, move further away from the strip. There's like 8 different degrees of motion with these air knives. It can move closer to the strip. They can move higher above the bath or lower. You can tilt them this way. You can get like an angle effect if you wanted to try that. You can skew them this way. If you see one edge of the strip is heavier than the other edge, maybe they're a little skewed or something. So there's a lot of different ways to adjust the coating weight in order to get a nice uniform coating. Yes?
How much time do you get back from that logic control?
Well, the response time is pretty quick. The problem is this is about, well, it's at the top of a 13-story building, so however many feet is that. I think it's like 150 feet or something. From the time it's coated, it takes probably about 20 seconds or something. The line's running about 400 feet a second, or 400 feet a minute, so whatever the math works out to. So there is a delay. By the time it actually reads it, it can feed it back, pretty instantaneously to what to change it to. But then to know if that change was correct, or to know if then it's got to wait for the strip to get back up here again, and it says, oh, okay, I'm happy, or do a little bit more or something. So there is a delay there, but it's a continuous line, a continuous strip. It shouldn't be very much change. I mean, across one coil, once it hits 60 grams at the start of it, it shouldn't really change very much to the end of it. There's no real reason to. The problem arises when you're switching coating weight aims from one order to another. If you're going from 60 to 90 or 90 to 60, then it has to make a pretty quick change. And at those transitions, there's actually logic in here where it'll kind of go and stop controlling it that way, and it goes into its own little, I forget what the proper word is, but it goes into its own little program and says, I know at this point I have to be at 60, because it knows the schedule, the computer has that knowledge, and it ramps up automatically till it gets whatever it thinks the proper pressures and all that is. And then once the coil comes in, it'll start reading it and see if it made it close enough. So it's not slowly reacting to it. When it knows there's a change coming, it has a program that'll react to that change and then kind of monitor it from there. So it's not just kind of slowly trying to get up to 90. It'll go to what it thinks will get at 90 and then try to measure it at that point. So the response time isn't really as bad as it may seem. Yes?
What sort of heat is maintained in that area?
Like I said, the strip was about 860 degrees. The pot's about 860. The strip, there's some cooling zones here because we want to cool the strip down because this is still molten zinc on there. So we want the zinc to solidify before it hits that turnaround roll. That's part of the reason why that building is so high is you don't want molten zinc on the strip when it hits a turnaround roll. Otherwise that roll is going to get all gunked up and be a mess. So there's like 4 or 5 different cooling zones up through here to cool it down. It's about 300 degrees. The strip is by the time it hits that roll. And this is a water-cooled roll that cools it down even a little bit more. So it's about 860 degrees here, about 300 degrees here. It'll come into the quench tank over here, and that cools it down to about room temperature, maybe 100 degrees or so here in the quench tank. So that's kind of the transitions we're looking at. This would make a nice galvanized product. Now we mentioned galvanneal and how that was made. So far, everything would be the same, galvanized galvanneal. The only difference is after you make the coating weight, it goes through the galvanneal furnace, which is a little furnace. Well, I shouldn't say little. It's a pretty big furnace, but it'll come online, and you can see that on your tour where the rails are. The furnace just comes online, surrounds the strip, and the doors will close on the other end, so the strip is going up through this little induction furnace, and that'll heat it up to about 1,025 degrees. And that's what's allowing that galvannealing to take effect that you saw in the samples there. So it's still molten zinc right here that just made the coating weight. Then you heat it up, allow that galvanneal to make, and then you cool it down through here until it's solidified, and then it hits the turnaround roll and hits the X-ray gauge. So that's kind of the processing there. So this is really the only difference between galvanized and galvanneal through the whole line is just whether you turn that furnace on or off. So it's not really a big difference as far as having a lot of extra processing done to it. The thing that does throw off galvanneal and the thing that makes it tricky is trying to measure the coating weight. Coating weight's for zinc are very easy. You can buy X-ray gauges from any place in the country to measure zinc on steel. The problem is trying to measure galvanneal coating is that now you have this iron in the coating and you have iron in the steel. So somehow the X-ray gauge kind of has to know when it gets a response from the iron and a different response from the zinc is, did that come about because the coating weight's thinner and I'm picking up the steel, or is there more iron in the coating? So there's a couple of manufacturers that make a gauge that does that, and we happen to have one of them. So we can actually measure the galvanneal coating. We measure the percent zinc in the coating, of course, for the coating weight, and also the percent iron in the coating. So that's kind of difficult for most lines to do. Most people, and it works fairly well, most people just look at the strip to see when they get a color like that. They'll just turn up their furnace from galvanized until they get a color like that sample and say, oh, I'm making galvanneal, and just kind of go on like that. And they'll measure a coating weight offline, you know, waste strip weigh or something like that. We can actually measure it online to make sure we're galvannealing it and getting optimum galvanneal, that we're not over galvannealing or under galvannealing. Under galvannealing is pretty easy to see because you won't have that galvanneal surface. It'll be, you'll have little spots of galvanize on it, kind of, or you'll have edges that are galvanized. Over galvannealing is just as bad. If you heat it up too much, it may look okay. It's still that nice dull gray, but when you go to bend it, it's going to powder a lot more. If you heat it up too much, you're going to have a lot more powdering on galvanneal. So there's a fine line you walk in making galvanneal between under galvannealing and over galvannealing. There's only a small window in there. So that X-ray gauge kind of helps us maintain us in that window. So we're not waiting till we get results back from the lab on the powdering test to see, uh-oh, we're really over galvannealing this, we better turn the furnace down. So we can kind of do all that online. Yes?
Does that heat affect the annealing or the hardness of the metal?
Well, we're kind of taking account of all that because in our annealing furnace here, you're kind of heating it up a little bit more, but you just annealed it, it's still 800 degrees here, so you're not affecting it anymore by annealing it here. No, it shouldn't change the properties. For the most part, most of the galvanneal we run is IF steel anyway, so it's pretty soft stuff. We do run some high strength and stuff, but that's all taken accounted for when you make the properties in the anneal furnace, as far as what you're going to do to it afterwards, if you're going to temper roll it and all that. You know, that's for people that set up the heat cycles, and I'm not one of them because I don't know all that. Take that into account, what's going to happen to the coil afterwards and what properties they need to make in the anneal furnace. So, does that kind of answer your question? I didn't really get to it, but okay, so now we've made either galvanized or galvanneal. We went through the quench tank to kind of cool it down. Then we get to our temper mill and tension leveler. It's a nice feature we have online. We can temper roll it and tension level it right online instead of having to take it and send it to our temper mill. You saw those galvanized samples, and I mentioned how it had a mirror-like surface when it first came out of the bath here, and we actually have to rough it up on our temper mill in order to get a proper matte finish. Everybody wants a certain look to their steel, certain matte finish or surface roughness, and that's where we would make it right here. We can put that matte on there. Tension leveler, some people want, order something very flat. We can make that right here. We also have the capability of putting a chromate solution on the strip for a chromate passivization. Some people want oil on the strip. Most people do. Some customers, mostly trade customers, want a chromate solution on there that helps it further from getting a white storage stain on the strip. Sometimes the zinc will actually oxidize and form a white rust on the strip. So if we put that chromate coating on, that helps prevent that. The oil will also do the same thing, but if somebody does not want oil and they're not going to paint it, they may want that chromate solution on there. So we have the capability, if it's a computer-controlled line, if they want it, the computer turns on the spray tanks and all that. If it doesn't want it, the computer turns them off. We come to the end of the line through the delivery tower, and then through the shear and the oiler and all the rest of that to get the coil off the line. We also have an inspection station, and you'll see it on your tour. The inspector is in a little room with the strip coming right up through the floor. So the inspector has the capability of looking right at the strip, can go walk around the other side, look at the bottom end of the strip, can walk all the way around it, as opposed to some inspection units where the strip is kind of running this way. And the inspector gets a real good look here, but on a 6-foot wide coil, he says, what's that little mark over there? And can't really see it too well unless he goes up over a walkway or something like that. So here the inspector can see the whole strip, walk around it, get very intimate with it in order to see any defects or whatever. Plus, they're in the same room with the operators, so they can say, hey, I got a scratch here or whatever, and they can try to fix it right away. So everybody's kind of in tune to try to produce a good coil. We also have the laboratory right underneath the delivery pulpit that does the adhesion checks, coating weight checks, all the line solutions for the chromate and the cleaner solution, the pot analysis, so we can get the kind of turnaround that's required in order to keep a continuous line running up to optimum conditions. Okay, let's compare that to the line I mentioned. We had a line outside of Buffalo, New York at Lackawanna. This line was built in the 1960s. It's actually called a cold flux line. Produces pretty much the same product, galvanized and galvanneal. A little bit different technology involved. It is a continuous line, so you still have the two coils here and a looping tower in the front and the back of the line. It still has a cleaning section. They still need a clean strip. And one thing they don't have is an anneal furnace. They don't anneal online like we do. So if they want all their coils, have to go from their tandem mill to their batch anneal to their temper mill before they can bring them to their hot dip line. So we have that efficiency of taking it right from the tandem mill to our hot dip line. They have to kind of send it to two other places, get it annealed, get it temper rolled, and then bring it to their line. So they don't have the annealing furnace, so they're not going to be able to heat it up to 860 degrees. We actually have to cool ours down, but they can't heat theirs up because it would change the properties they made back in batch anneal. So what they do is apply a flux to it, hence the name cold flux line. It's actually like a welding flux, ammonium chloride kind of solution that's going to attach to the strip. They just kind of put it through a little dip tank, and that's going to help the zinc stick. That's going to form the bond between the zinc and the base metal. At this point, it goes through their zinc pot, pretty similar to ours. It just goes through the pot, gets the zinc applied, comes up through their air knives. They have a galvanneal furnace. If they want to make galvanneal, they bring it online. If they don't, they take it offline, just like we do. Theirs is actually a gas-fired furnace, whereas ours is an induction furnace. Small differences, but a little bit of difference there. That's why you notice their product looked a little bit different than ours, because they have a different annealing setup. They have a different annealing or galvannealing setup. Things are a little different, but it still makes a good galvanneal product. Comes up to their coating weight gauge. Every hot dip line in the world's got a coating weight gauge. Not all of them can run galvanneal. This one can't run the coating weight in the percent irons, but does a real good job on galvanized, and they know through the history how to make galvanneal. And that's probably the way it is on 90% of the coating lines across the country. Come down. One other thing they don't have is a temper mill. So if they want to put a matte surface on it, they have to send it back to their temper mill again. So whereas at Burns Harbor, we can anneal it, coat it, temper roll it, ship it out the door, they have to send it to be annealed, put it on the coating line, send it out to be temper rolled, and then ship it out the door. So we have a lot of efficiencies that they don't have there. The one thing this does get you, though, is they have the flexibilities that we don't have. Since we're doing it all in one operation, we're kind of limited in the kind of steel grades we can use, some of our gauges and thicknesses and strengths and stuff. They're fairly wide open on their hot dip line. You saw that first sample that went around, the spangled one, how thick that was, how heavy the coating was. We couldn't produce that on our line here. There's some grades and stuff and combinations that they can do better than us, just because we're limited in being efficient. So that's some of the trade-offs. So it's actually good for us to have a line of each capability. We have the efficiency here, and we have the flexibility there. So it gives us kind of a two-edged sword kind of deal. They can put chromate solution on it just like we can. They can put oil on it, all that kind of stuff. So,
Dave?
Yeah.
On Lackawanna, we're in the process of talking with Bethlehem to make a non-IF product. And they're saying it has to go to the Lackawanna facility. Could you explain the difference between non-IF and IF? And if I go non-IF, why do I got to go there?
You're trying to make like DDQ or something, or?
I'm not sure.
DQ?
Not sure.
Since we anneal in line, we use IF steel probably 90% of the time. And part of the reasoning is with IF steel, you don't get yield point elongation because there's basically no carbon in there. So you don't get that orange peel that you may see from the yield point elongation. So the physical properties, after you temper roll it, you could get some strain aging, as it's called, and get that yield point returning. With IF steels, you don't get that because there's no way you're ever going to get it. If we produced a non-IF steel off our hot dip line, we don't have let me see how to explain this, because I'm not a metallurgist. When Pete was talking about the CHTL line this morning, how it had that overage section on there, that was to eliminate the yield point elongation from returning through that strain aging. Our hot dip line anneal furnace does not have that overage section. So if we were producing it on a line, if our hot dip line did have that overage section, we could run IF or non-IF, it wouldn't matter. Since we don't have it, we're kind of limited to running IF, so we don't get that yield point elongation returning, or the strain hardening returning. Lackawanna, since they anneal offline, and they batch anneal their product, they don't have that problem. They can run any kind of gauge, and that's part of the flexibility that they have, is they batch annealed offline, and then they temper-roll it when it's done, so they don't have that strain aging returning. So that's kind of the reasoning, and it goes back to that flexibility versus efficiency, and giving us the way to go either way on it. If we only had that one line, we couldn't do it. So I don't know if that answered your question. Like I said, I'm not a metallurgist, but
I'm still not clear on the advantages of non-IF vis-a-vis IF.
I don't know if there's any advantages. I mean, the properties, depending on what you're looking for, say you're looking for a DQSK type properties, an IF steel off of our hot dip line will give you very good DQSK properties. A regular DQSK steel off of Lackawanna will give you very good DQSK properties. So I don't think there's much difference in what you're going to end up with. It's just a matter of how it's being produced. So yeah, you might want to ask one of our product application guys or something. I don't know who you have dealings with, but that's kind of the basic reasoning behind it, is because we're limited here in the way our anneal furnace is set up without that overage section. So I don't know if that answers or okay. Kind of tap dance my way around that one. Just to kind of summarize our hot dip line here, the primary market on the line is automotive. That's why we went with the no spangled look as opposed to that spangled product, because it gives us the flexibility actually to do both automotive and non-automotive. It's rated at 450,000 tons a year. Actually, the last 2 years we've been over that number. We've been selling out the line basically. We can go up to 72 inches wide, up to 08 gauge. The Lackawanna line can go up to about 125 gauge, I think. So there again, there's flexibility of being able to go to thicker gauges. Some of the products that we make coming off the line, yield strengths up to about 60. We can make galvanized and galvanneal. In our coating weight range, we go up to about G90. Lackawanna can go up to like G150 or something like that. For those of you that aren't really familiar with coating weights, there's basically two systems. Just like everything else, there's an English system and a metric system. When you see something that says G90, that's the English system. It's kind of the, I don't want to say old-fashioned way, but that's the way most people are used to talking about it. And what that means is you actually have 0.90 ounces per square foot total on the strip. On top and bottom added together would be 0.90. In that terminology, there's no way to say you actually have 0.45 on the top and 0.45 on the bottom. That's what you're aiming for, but that's not the way you order it. You order at 0.90 total on both sides. In the metric system, you would see for the equivalent weight would be like a 61G/61G. And that means you got 61 grams per square meter on the top and 61 grams per square meter on the bottom. And you can actually designate how much on top and bottom. So if you want it more on the top than the bottom, you almost have to order it through that metric way. So you can say I want 60 on the top and 90 on the bottom. Through the English method, there's no way to actually do that. So it's just something to keep in mind when you're talking to somebody about coating weights. Whether they say G90 or 90G, it makes a difference. So it's just something to keep in mind again. I'm sorry, the equivalent of that would be 137G over 137G. That'd be the metric equivalent of a G90. So. Yeah, a short movie I'd just like to show you of our hot dip line. It's only about 5 minutes. You will be going on a tour of it, but this kind of gets you to think about some of the other things that happen on the line. It probably explains it a little bit better than I do.
Sheet steel products that stand up to tough environments. Corrosion-resistant sheet that makes automotive products look good and keeps them looking good. When it comes to coated sheet products that stand the test of time, Burns Harbor has it covered. Bethlehem Steel's Burns Harbor division produces top-quality steel in the most modern facilities in North America. Our steel is chemically precise to meet customers' exact specifications. Our continuous casters and rolling mills turn out clean, flat sheet with consistent thickness, width, and formability. This first-class substrate is the feedstock for our coating lines. Burns Harbor operates several coating lines to serve our automotive customers, and here is the newest one, our $200 million hot dip coating line for galvanized and galvannealed sheet products. From entry end to the shipping dock, this line is state-of-the-art, built in direct response to our automotive customers' needs. The line is computer-controlled, monitored for consistency and quality every inch of the way, and it's operated by a world-class team to give our customers a competitive edge. World-class coated sheet starts here with top-quality coils from our cold tandem mill. The hot dip line's dual entry reels provide a steady supply of steel. As steel moves into the line, X-ray thickness gauges and an entry end shear ensure that our customers receive sheet with uniform thickness. A narrow seam welder joins coils from the entry reels, producing high-quality welds with minimal thickness. An entry looping tower permits continuous operation of the line with no slowdowns or interruptions for coil changes or welding. This means uniformly coated, consistent finished product for our customers. A three-stage cleaning system, including an electrolytic alkaline cleaner scrubber, ensures clean sheet for a smooth surface and excellent coating adhesion. Next, the steel loops through the all-radiant tube furnace, where it's heated to impart consistent final mechanical properties. The reducing atmosphere also improves coating adhesion. From the furnace, the sheet moves into the heart of the line, the zinc coating pot, where it gets the corrosion-resistant finish that adds good looks, long life, and value to our customers' products. As the sheet leaves the bath, our precision coating weight control system ensures a uniform coating. This flexible hot dip line offers both galvanized and galvannealed coatings, with easy changeover from one product to the other. The induction galvannealing furnace ensures uniform alloy coating and resistance to powdering. High above the zinc pot, our coating thickness gauge scans the full width of the sheet, top and bottom, and continuously feeds information back to the coating weight control system. More assurance of uniform coating and precise alloy control, edge to edge, throughout the length of the coil. After the sheet is coated and cooled, an inline temper mill and tension leveler are available depending on customer requirements. The 4-high temper mill and the tension leveler provide excellent shape and flatness and superior surface finish. The coating gets a thorough visual inspection as it passes from the exit looping tower to the dual exit reels, and the dedication to quality continues after the steel leaves the line itself. The coils are carefully packaged according to individual customer preferences. To avoid damage, we handle finished coils with an anti-sway crane block and store them on protective coil saddles until shipped. This is Burns Harbor's new hot dip coating line, delivering our automotive customers great looks and outstanding protection on a world-class steel sheet. And the commitment is the same at all of our coating lines. Superior flatness, superior coating, and superior surface. Superior quality and value for our customers. For coated sheet products that stand the test of time, Burns Harbor has it covered.
Okay, we're going to shift gears a little bit, talk about electro-galvanized. We talked about hot dip galvanized and how great that was, and now we're going to talk about electro-galvanized and how it's even better. Some people think it's better, some people like hot dip better. You get a lot of controversy of which one's better product and all that, and each one has its advantages. Electro-galvanized is a lot more expensive. If you need those advantages, then you have to pay the price. If you can live with the hot dip galvanized, then that's the best product for you. So, just to kind of summarize where we're at here, because you've kind of been jumping all around the cold mill, If we started off in the hot mill, which you saw yesterday, producing the hot bands that went through the pickler to remove all the rust, went through the tandem mill to get the proper gauge, and you'll see this part of the tour today. The tandem mill, if it went to the hot dip line, like we just talked about, it would go off here into its own little line, go into the hot dip line. As Pete was talking about this morning, the regular cold roll product would go to either continuous anneal or batch anneal, depending on what was required. After that would go to the temper mill, and you'd have your fully produced cold roll coil. At that point, it's where the electrogalvanized comes in. So electrogalvanized is actually coating a fully produced, A1 top of the line coil that's been through all the cold mill processing. Could go out the door to be a cold rolled roof or something like that, except for now we're going to put some zinc on it. So that's where the stock comes from for electrogalvanized products. Actually a finished coil with the finished surface roughness, the finished properties, everything you want on it's already done to it. All we're doing is putting zinc on it over top of it. So let me hand these out so we get them passed around before we finish up here. This is the electrogalvanized sample. Nice dull gray. Kind of looks a little bit like the galvanneal product, looks a little bit like cold rolled. Doesn't have that nice shiny surface that galvanized does. And this is another product we'll talk about a little bit, is the zinc nickel product with a universal coat, or what they call a UC coating on the back of it. So just to let you know, that's another product that's available. All our electrogalvanizing is done at a line outside Toledo, Walbridge, Ohio. It's a joint venture with Inland and Prefinished Metals. So we send all our coils out there. They either get a zinc coating, which was the first sample, or that zinc nickel coating, which is the second sample. But they all get sent out to Toledo. Kind of compare some of the reasons and some of the benefits of electrogalvanizing to cold roll and to hot dip. And some of these I agree with more than others. I kind of inherited some of these slides, so I'll editorialize as we go through. Excellent surface quality. It's only as good as the surface quality going into it. So if you have an excellent surface quality coming out the temper mill, when you electrogalvanize, you'll mimic that surface. So if it's a good quality, this won't make it any worse, hopefully, unless they have a problem coating it. But it should mimic that. So if you have a good surface coming in, you'll have a good surface going out. It should be the same type surface, the same roughness, the same look to it, all that kind of stuff. So yes, excellent surface quality, especially as opposed to galvanized. You saw the galvanized, just basically molten zinc on top of steel. This is electroplated, so it has a much better chance of making that good surface. Exceptional coating uniformity. I wouldn't say exceptional. Electrogalvanized is a more uniform coating than hot dip galvanized. And especially 10, 15 years ago, it was an exceptionally better coating as far as uniformity across the strip. It's a lot easier to control the plating with electricity than to control it by blowing air on it. It's kind of a rudimentary way to do it, just trying to blow off excess. With the hot dip lines that are coming up to speed now, with the computer controls and the different modes of freedom and all that kind of stuff, hot dip coatings are approaching electrogalvanized as far as uniformity. Not there yet, but they're getting there. So if that's something that's very important to you, then electrogalvanized would be your choice. If it's something where you can live with a little bit less uniformity across the strip, then EG may be good enough for you. So they're kind of closing that gap. EG is still better, but it's not as wide as gap as it used to be. More manufacturable than hot dip in some ways. Better forming kind of depends on how your process is set up. The coefficients of friction and all that are a little bit different between electrogalvanized. Electrogalvanized is kind of more like a cold roll product, whereas the hot dip and galvanneal are a little bit different as far as their coefficients of friction and stuff. So it kind of depends on what your process is set up on, but there's some advantages to being a little bit better formability. Better coating adhesion, better than galvanneal, definitely. We talked about galvanneal and the powdering problems. If you over galvanneal it, electrogalvanized, basically it's not going to come off. It's electroplated on. It's not going to come off. You bend it and form it. However, in galvanized, the coating's not going to come off either for the most part, unless you're really deforming it. But you can break galvanized and not have the coating fall off. So between EG and galvanized, pretty similar adhesions. Galvanneal definitely worse. Better welding. It's better welding than galvanized. But galvanneal, we talked about, the reason you get galvanneal is to get better welding. So Galvanneal would be top welding, EG, and then hot dip. So there's kind of some play in there. Coating flexibility, well, if you want EG, then it's very flexible. If you want hot dip, then it's not the way to go. But you do have the choice of either making the zinc coating or the zinc nickel coating that's going around, so you have that variability. Vary coating weight, electrogalvanize, just like EG. You can decide if you want 60 grams on top, 30 grams on the bottom, or whatever combinations you want. The advantage of electrogalvanize is you can do a one-sided coating. And there used to be a big market for that where you just want one-sided zinc coating. And hot dip, you couldn't do that because it's coming through molten zinc. You're always going to have something on one side. Maybe you can blow real hard and get it as low as you can, but you're always going to have two sides zinc coated. So if you only wanted one side, then you'd need electrogalvanize. The base metals available, kind of the same on both of them between hot dip and EG. Compared to our hot dip line, we are limited, as we talked about, our need for IF steel based on our hot dip line. Electrogalvanize, basically anything you can cold roll, you can electrogalvanize. So it has a full wide range of different grades and things like that and strengths going into it.